We are here.
Because I've been known to forget, and now I don't have to remember anymore.
We got it.
Okay. So, all right, it's 7:59. It's almost time to start. Here's a really good time for people to ask questions based on yesterday. So if you have questions based on yesterday, now's a really good time to ask. And remember, there's no such thing as a dumb question other than the one that you never bothered to ask.
That's right.
And if you're thinking it, somebody else is probably thinking it too. So fire away. We actually had a pretty good discussion after most people left yesterday too, which we're going to end up doing a repeat on, but we got into some pretty heavy talk about antennas and arrays and phasing and things like that. So
I have a test question.
yeah.
So I'm scheduled to take tests at the end of the week. I know I have to, I read all the do's and don'ts, right? I have to show them the room. I'm in my office right now. So there's another computer here with another camera that can watch me, yada, yada, I get all that, right? Obviously can't have notes or anything like that with me.
Right.
Once the test starts, sitting here at my desk, I have a magnetic blotter, whatever you want to call it, because I'm a police chief. I work on people's firearms. I'm also a Glock armorer. It's also dry erase. I could write right on my desk. I could take notes on my desk. Once the test starts, can I write down Ohm's law on my desk? Or...
Well, I would say that typically we use a piece of paper.
Okay. Also, I could have scrap paper.
You can have a piece of scrap paper. Yeah, you have to prove.
I can write it down right away. So
yes, you get one sheet of paper. And you can write anything you want on it as soon as the test
has to be blank when it starts, correct?
Yep.
Okay, cool. That was my one. So like first thing I do, I could write Ohm's law down and then just forget about it and keep going, right?
That's what I used to write that when I took a physics exam. That's what I used to do. If there was something that I knew I was going to forget, I would scribble it down so I had it written down.
Okay, perfect. Thank you.
For the testing agreement form, are we doing a fully remote examination?
Yeah.
All right.
Yeah, in fact, I remember this one physics exam where 5 minutes before my test, I said, I bet he's going to ask something about this. And it was some really, really obscure equation. And it was like, I remember because it had a component of 3/8 in it, which was really strange. And I just remembered it. I just did it over and over and over. And so was scribbling it down. I'm like, okay, as soon as I got the test paper, they said, you may begin. I just wrote it down and then I just forgot it. But then later at the end of the exam, I actually had to use it and I got it right. So yes, I'm a firm believer in that. And I don't remember the equation, but it had 3/8 in it. I remember that because it was so weird.
I got part of your stuff yesterday after the meeting, but 4 hours is a long time for me to sit.
4 hours is a long time for me to talk.
Well, I don't know how you can do it. I really don't.
Normally I do 8.
Oh.
The first day is 8. Yeah.
Scott, this is a very sort of off the wall question, but the 30 to 300, 300 to 3000, etc. Is that 3 based on anything?
Yes.
Okay.
If it had to be based on something, what would you guess it's based on?
I would guess it was based on decibels.
Nope.
Okay.
Well, remember that we're talking
Wrong
about
again.
we're talking about wavelengths and speed, wavelengths and frequencies.
Oh, yep.
So where does that 3 come in? You remember something that has a 3 in it?
Yeah, speed of light.
Speed of light. Yep.
Okay. I just
So
didn't
that's
know
where
what
we
to
get that.
connect it to. Thank
So
you.
3 to 30 megahertz again is HF, and then VHF and UHF. All right. So any guess what the remember what below it was called? That was actually MF, medium frequency. And above that is SHF. So medium frequency, high frequency, very high, ultra high, and super high. They kept running out of names, because after that is extra high. And then below this is low frequency. So, which is really funny because you think of high frequency. Well, they figured out, oh, there's something higher than high. Okay, and then the ultra high.
Scott, could you explain the difference between wavelength and frequency?
They are like so if this is a wave, this is physically the length. It is the physical space. So that is the physical distance of a wave. That is the wavelength.
God.
And the frequency is how many of those occur in 1 second as it travels this way.
And so the basic, the beginning is the end, at the end is the beginning.
Yep. Because that carries together. Okay, well, if I know that it's going to go 300 million meters in 1 second, and I know that it went this many meters every time it did that, every time it made one full wave, because this is the wavelength, then how many of those occurred in 1 second? So it's just a simple division because of that.
Thank you.
Mhm.
That explains it.
Other
Scott,
ones, yes.
we talked a little bit yesterday about decibels, and I struggled to wrap my mind around those. I ran across a question studying last night, so here it is. It
Mhm.
said it said how much power increase does your transmitter have to do to move from S8 to S9?
Okay,
And the answer was 4 times.
that's right. Okay,
But I don't.
Here we go.
I don't.
Well,
get that.
here we go. We're gonna do this right now. Okay, so there's 2 things that you have to remember. 10 decibels is how many times?
10 times,
10
10.
times. Okay, and 3 decibels is
twice.
twice.
One.
Okay. So by convention, 1 S unit is equal to 6 dB on your receiver scale. That's by convention, by basically agreement of all the manufacturers that have ever made anything. 1 S unit. So if you look at your meter, it'll say S0, 1, 3, 5, 7, 9, and then it'll say plus 20 dB like that. So to go from S8 to S9 is 1 S unit, which is 6 dB, right? So if it's 6 dB, that's 3 dB plus 3 dB, which is 2 times, and 2 times is 4 times.
Oh, that's pretty clear now. Thanks.
Other ones?
The
What
test is 35 questions?
What is the name of the symbol you use for the wavelength?
Lambda,
Oh, Lambda.
Greek letter
Lambda,
lambda.
Thank you.
I know Steve knows that. Greek
Yes,
and Latin, right? From Greek.
right,
Yep.
right.
And actually it gave that lambda, actually that same letter, it shows up in Cyrillic. It also shows up in Hebrew. It's
But lambda is the Greek L in the
yeah,
Greek
lambda
alphabet,
is the Greek L.
and that's the pronunciation of it.
I was trying to
So-
explain it to my parents and I was like, it's a half kind of TP, weird, long, short, anyways, lambda. Thank you.
That's a lambda.
So does that simply come from length?
It's whatever they wanted to do it. It's, you know, a lot of these things, you know, how do they come about? I don't know. Probably. And they'd already used L for something, so that would be my guess.
Well, the Roman L stands for inductance, right?
Yes, it stands for inductive, the capital letter L. And sometimes I'll do like a little script L for length, so. Any other question?
Scott,
Uh-huh.
can we use a calculator?
You can use a dumb calculator. You can't use a smartphone or a watch.
Oh, okay.
But if you have a dumb 4-function calculator, add, subtract, multiply, divide,
something like this.
Can we use like one of
Just like
the
that.
scientific ones from high school or middle school?
It depends if it's programmable.
Last time they checked my memory, if there was anything stored in the memory and stuff.
Yeah, exactly.
So isn't it useful? I'm gonna have to go out and buy a dumb calculator, as you say. Don't I need to get one that can do a square root calculation?
If you're taking the general
Useful.
exam, yeah, it's like, yeah. Most of those 4-button calculators will have a square root. You know, those 4-function calculators. I think. Mary Ellen, can you hold up? What, you were the one with the calculator? Can you hold it up again?
Sure.
Hold it up real close so we can see the buttons.
1 minute. Let's see.
Can't see it.
Oh, okay. Let's see. 1 minute. I'm trying to angle it.
There we go. Up a little bit to your right. And yep, there's a square root at the lower left.
Oh, okay.
Can we use one like William has on his screen?
Let me kill my pin. Hold on. Remove pin. A TI. Well, let's see if I think that's fine. If
Okay,
you
word.
can-
Yeah, exactly. I literally bought one last night just for this.
Yeah. I think that works. If you can show that the memory is empty, because I know that TI-30 is not programmable.
My memory says that most of the questions, if you just estimated, you could get close enough to eliminate
Oh yeah. Yeah.
almost everything.
Yeah. You don't, I mean,
Um,
honestly, you don't really need a calculator, and no, you can't use the calculator PC, the PC calculator. You're going to be in, you're going to be in full screen mode. So you can't use the calculator on the PC.
Question, when I give GLARG tests, we were allowed to, let the students use the one on, we would look at it, the one they had on their desktop, and they could use that one on their desktop.
Yeah, I don't,
And that was using the GLARG remote test.
okay. To my knowledge, the Anchorage group doesn't allow that because it runs in full screen mode and they want to see full screen.
Yeah, we look at their screens anyway, but. yeah,
Right,
that's on
right.
With my luck, my computer would freeze on me and I'd have to restart again. It did it 4 times yesterday at the beginning of the class.
Yeah, well, hope no more today. Today's going to be good.
Yeah, so far.
All right. Any other questions before we get going? If you received a note, if you signed up for an exam and you received a note that said, hey, your exam registration isn't complete yet, you're going to need to go and complete it. That would have been sent by email. So
Yeah, I did that yesterday.
good.
Yep, mine's ready.
Okay. You guys ready to start?
Yep. Let's keep
Okay.
going.
So
Let's rock
today,
and roll.
okay, so today we're back to that section of the book where we are looking at this right here, where it says electronic components and circuits. Right now, we already started doing circuits, but we're just going to cover this. And in my PDF, it's on page, the 23rd page of the PDF. If you're lucky, you've got a version that actually has page numbers, and I don't know that I do still. Okay, electrical component, and if you know the answer, just blurt it out. Electrical component opposes the flow of DC in a circuit.
Resistor.
That's a resistor.
Resist it.
Okay, so a potentiometer is a variable resistor.
Current monitor.
Yep.
I mean meter.
Potentiometer. That also has another name, which it looks like this. It can actually be drawn like this. That means it's a variable resistor. You can also draw it like this. Sometimes you'll see it look like that. Basically allowing you to select part of the resistor. So this is also known as a pot or a potentiometer.
And what would we use that for?
That's a variable resistor. So let's say you wanted to adjust. Let's say you had a battery here and you had a resistor right here and you had another one right here, and you use this as a potentiometer and you picked a voltage off right here. This is a voltage divider, R1. We'll call this R2. If you can vary R2, what does that mean you're going to do to your voltage right here? Because this is a voltage divider. It divides the voltage based on the values of R1 and R2. So what does that mean if you can vary one of them?
You can adjust it.
You can adjust your voltage. So you can have an adjustable voltage, for instance. It can also be, and typically this would be a linear thing. So if you turn it, let's say it's one turn, if you turn it halfway, you'd get half the resistance. The other very common use for a potentiometer is a volume control. And because when you turn the knob, you want the let's say you turn the knob halfway, you want the volume to go up halfway, and so on and so forth. This is actually because sound pressure increases logarithmically. This is actually a this is a linear control, and this is a logarithmic control. So a volume control is it's a different ratio. So just to know that if you swap one for the other, it's going to act really weird.
But then if you calculate with a variable resistor in your circuit, if you go to calculate total resistance and you drew that circuit showing that the resistors were in series.
Mhm.
So it would still be, the total resistance would still be the sum of the two, but would depend on how you set the variable resistor.
Yep.
What about if they're in parallel?
Well, if they're in parallel, it doesn't make any difference. Okay, let me ask this. Let me ask this question. This is the next one. If I go like this, and I have a variable resistor that goes like this, this functions as a current divider, right? It splits the current.
Yeah.
Okay. Well, let's say that I wanted a certain amount of current to flow no matter what through R1, and for some reason I wanted a variable amount of current to go through here. Well, okay, I could vary this resistor, and that would change the amount of current that I get through there. But in reality, I don't need this first resistor at all, because they're in parallel and they don't affect each other.
But
Actually, I take that back. They do, because the current gets split that way and that way.
Right.
So whatever you don't take into R2 has to go to R1 because it
Correct.
all has to go somewhere.
Right. Has to go somewhere.
Yes, have a
So-
load.
Right. So if I increase this value to infinity, how much current goes through an infinite resistor? An infinite resistor is also known as an open circuit.
And
Zero.
None.
Zero. How about if I do this, short it? How much of the current
Max
will go
current.
through there?
all of it.
Yeah, all of it. You'll get nothing through R1. Because
So
current follows.
there has to be a pot to assign to each resistor.
No, it doesn't have to be. I mean, but what if I don't care what the resistance, what the current through the first one is? I just, have it as a baseline or something. It kind of like sets a base value. Then the second one can basically, in other words, like it allows me to limit. Okay, here's a way to do this. So let's say I have two resistors in parallel. And this one is 10 ohms. And this one is 10 ohms. What is my combination resistance for these two?
5,
Don't say 20, because they're in parallel, right?
5,
Yes.
So that's 5 ohms. Okay. What if I were to drop this down to 1 ohm? Well, the formula for this is R1 times R2 divided by R1 plus R2. So it's 10 times 1 divided by 10 plus 1. 10 over 11.
like 0.9.
Yeah, it's like 0.9 ohms. So what this resistor does here is it keeps this one from going all the way. You know, they basically affect each other. Now, if I were to make this one 100 ohms, I'd have to do the calculation again. 10 times 100 divided by 10 plus 100 equals to 1,000 divided by 110, which is about 9 ohms. So by varying this resistor here, what it does is it basically severely affects what happens to that 10. Well, it can go all the way up to, it can go all the way up to 9 ohms now, or it can go all the way down to almost 0. So. All right, let's see, where were we? We are on, there we are. What electrical parameter is controlled by a potentiometer? That'd be resistance. And remember, resistance is the opposition of what kind of current flow? AC or DC?
DC.
DC, okay. Now, we're going to get to this in just a second. The opposition of current flow to AC current is known as impedance. Now, as we looked yesterday, does a resistor care
No,
whether or not it's AC or DC?
no.
Nope, it does not. Okay, so now we're going to get to capacitors. So when we talk about capacitors, we are basically talking about two metal, typically conductive plates that are connected like this. And what does it look like is in between them?
Nothing.
Nothing, exactly. There's nothing. There's empty space. Now that doesn't necessarily have to be empty space. That could be filled with plastic or tantalum or polyethylene plastic. It could be filled with mica. It's basically something that is not conductive. So it's an insulating material. It could be glass. It could be air. So what we're going to do is we're now going to draw a battery. And we're going to hook it up to this capacitor. Okay, so we have a plus terminal and a minus terminal. And now we're going to talk about the fact that where do the electrons come out of, the plus or the minus?
The plus side.
No. Remember, they got it wrong. Where do the electrons
Oh, it
actually
was the
flow out of?
minus, right?
That's
Yeah.
right. The electrons come out of the minus terminal. And therefore, because there is no such thing as a plus charge in this case, the plus term, the electrons that were over here on the left side are now attracted to the positive terminal. So all those electrons that were over here are now, or that were on that plate, are now over here. Because this was a neutral piece of metal, the assumption is that this particular plate and this particular plate originally had a net charge of 0, right? They weren't charged up. But now we've pulled all the electrons away. And since we pull all the electrons away, what are we left with? We pull all the minuses away and we're left with an excess of positives, which is a lack of negatives. So what we've done is we've now created an imbalance right here. Okay, so now what do we have is this imbalance. These plates are now charged. One of them is holding minuses, the other one's holding pluses. What do they really want to do?
Join.
So there's two ways for them to do that. Number one, what's number one?
Cancel each other.
Yeah, well, how would the electrons get from one side to the other?
Transfer charge or jump.
Yeah, they could jump. That's right. They could go whoop from one side to the other. And what is preventing them from doing so?
The non-conductive material in between.
and the fact that it's a space, right? So there's a non-conductive insulating material right here, which is known as a dielectric, which is preventing the electrons from making that jump. There's another part of it, the fact that those plates physically want to join together because now the electrons and the lack of electrons are sort of pulling. These generate that pull actually generates a force. This is an electric field. That generates an electric field, which wants to pull those plates together. So if you think about it, if you're halfway in between, let's say that you're standing right here, what are you going to notice if you can sense electricity?
Heat.
Well, what are you going to notice? Nothing's moving, but you're going to notice that.
Sparks?
Yeah, well, hopefully not.
That
Hopefully,
buzzing sound.
yeah, well, no, hopefully you're not going to actually notice anything, but you're going to notice, if you could measure it, the fact that the electrons and the lack of electrons really want to get together, right? There's going to be tension in there.
You're going to see
Right.
some movement.
Well, ideally you won't see any movement, but you'll feel like there should be. These
Well, if
things-
those are plates, won't they try to come together?
but they're now how are they going to be kept apart?
The dielectric.
The dielectric material that's in between them is going to physically separate them, and it's actually going to fill the space. So they can't move those. You can't move those plates together. If it was strong enough, sure, you could actually crush it. But ideally, this space is now rigid. So there's going to be a tension that builds up in there. And if you're in the middle of it, you can feel the tension, right? That is the electric field that exists between the electrons and the side with the lack of electrons, right? This is known as a capacitor. And a capacitor stores energy in an electric field. So a capacitor is an electric field energy storage device. So now, because we've stored energy in this electric field, right? We're now going to take this battery and we're just going to remove it. Okay, what are we left with?
Stored energy.
Stored energy, yeah. Does it have anywhere to go?
No,
Nope. When does it have somewhere to go?
When you connect those two dots on the bottom, they become the terminals on your battery.
Or if you were to do this and get these two terminals really close together, what would happen?
spark.
It'll arc
You get a spark.
across.
You get an arc right across. This is how an old school ignition system works. You charge up a capacitor, and then you use your points and you put the spark plug, you put them really close together and you generate a voltage, right? That's one way to do it. That's a capacitor. Now, there's another way to look at this, which is now we're going to take this capacitor. We're also going to get to an inductor in a second. Okay, so a capacitor is an electric field energy storage unit. And I actually once took a big capacitor, which looked like this. Whoop, whoop. Plus, minus. I charged it up to 9 volts. It had a value of 500,000 microfarads, which is actually an enormous amount of charge. The unit of storage for a capacitor is known as the farad, named after Michael Faraday. A capacitor is listed as a letter C, and the units are in farads, which is F. The ability of something to store charge is, oddly enough, capacitance. You might also see this thing listed as a condenser. This is an older school term for a capacitor. So I charged up this capacitor to 9 volts. I said, well, I better discharge it. What would happen if this suddenly had a short circuit across it? If I were to jump this, what would the charges immediately do?
They'd equalize.
They would equalize. You'd basically have an enormous amount of current. All the electrons in an uncontrolled fashion would basically go to join the lack of electrons, and you'd basically balance it out. You'd have no charge. Okay, so what if I was young and stupid and did not completely understand electrical stuff, and I took, instead of doing that, I took a pair of screwdrivers, and I went with one of them, I did this, and the other one I did this until they touched.
You'd weld the two screwdrivers
You
together.
would weld two screwdrivers together, which I basically did, using just a capacitor with a 9-volt battery. It was pretty cool, except I destroyed two screwdrivers that way.
Is that similar to when we used to have to jump the solenoid in an old Ford? Same idea?
I don't know, but that's basically arc welding.
Well, yeah, and you would, if you just touched it to get, if the solenoid in that Ford stopped working, you jump the current across them to get the starter to engage.
Yep, I gotta do that with my go-kart.
Stop now.
There you go.
There you go.
So 9 volts is a little bitty battery, right?
9 volts is a 9-volt battery, but it's not about the voltage, it's about the number of electrons stored. Because current is what?
B equals IR.
Flow of electrons.
So Scott, is a wet cell battery like we use in our automobiles, is that a giant capacitor?
You can think of it like that. It's but except that it's a chemical storage capacitor.
It's a
Because
chemical storage.
because it's stored in the chemistry. But you can also have like an ultra capacitor, which has a very high capacity for storing energy.
Right, and this is not a bridge.
So for a very short time, I probably generated 1,000 amps when I shorted those two things together. It made a very big blue flash, and it was hot enough to basically weld two screwdrivers together. They pulled apart, but I was left with little pooled pieces of pooled metal, chrome, vanadium, steel. So there was just, there was a lot of current available because there was very low resistance. Again, E equals I times R. Everything comes back to Ohm's law. So 9 volts across a 0 resistance, how much current can flow?
All of it.
E I R. Well, so E equals I times R. I equals E divided by R. What is 9 divided by 0? That's infinity. So basically I got as much current as could possibly be delivered by that capacity. And that is basically then determined by the fact that capacitance is equal to Q equals CV. Q is the amount of charge on a capacitor. So the capacitance times the voltage at which you're charging it. And then Q is an amount of charge, and current is equal to Q divided by time. So if it happened really fast, I had a big charge because I had a big capacitor in a very, very, very short time. So I probably had, 1,000 amps for a really short time.
So somehow I'm missing out on the concept of how much stuff you can shove into a little bitty 9-volt battery.
It doesn't matter how much you can stuff into it. A 9-volt battery is a chemical storage device. It actually can produce, because of its chemistry, a lot of electrons.
Okay, that's where I'm lost. We'll come back to it later, I guess.
Well, I mean, it basically, any battery has a plus and a minus chemistry, right? That when you basically you have two terminals, and you keep the chemical 1 apart, it's in contact with the chemical 2, and it generates an electrical potential between the two. So here's the 1 and here's the 2. So that would be the plus and the minus terminal. And once you give the electrons that are being made a way to come out by hooking it up to a wire, the chemical reaction is allowed to happen between the two sides. So that's why you'll see like an alkaline battery.
And there's a potentiometer called a volume control, or light switch or something in between.
Yep.
To adjust the flow.
Yep.
Of electrons from one side to the other.
Yep. Or
When
if you
you
have a
get-
lead acid battery, that's a combination of lead and sulfuric acid. If you charge it, you basically can reverse the chemistry. So you have an excess of electrons stored. If you use it up, there are no more electrons to be dumped out. So it's reversible. But essentially, that's what a battery is. It's an electron generating device because you've stored it in there through chemistry.
Scott, this may not make any difference, but I noticed when you are sharing your screen, I read at the top of my screen, you are viewing Karen's iPad.
Oh, yeah, that's my wife's. I can,
Okay.
I can change it. Here, I'll
I
change
thought
it.
that was Karen in our group.
Oh. There. Okay, much better. Okay. You ready to go back to this? So now we've got a capacitor, right? Okay, so a capacitor is an electrical storage device, stores energy in an electric field. The ability of a capacitor to store energy in an electric field is capacitance. The unit of capacitance is the farad. Notice there's inductors coming, but we're actually going to take a little bit of a shortcut. All right, so we're going to do inductors right now. Okay, so if you think about electromagnetics, you have electric field and magnetic field. Well, this is an inductor. It's measured, its letter is L, units are henries. And those are letter H. So you could have 0.003 henries. That's a measure of inductance. So in order to do this, what we have to understand is that a piece of wire, if you hold up your right hand, stick your thumb out, and then roll your fingers forward. So a current that goes in the direction of your thumb will make a magnetic field that rotates around the current. So if you have a wire that's carrying current this way, then you'll have going into the page. Notice I have a little X's. That means going into the page. And here I have a dot. That means coming out of the page. So it can connect the dots like this. So that is the direction of my magnetic field. And you can, if you ever run into like, how does that happen? You just remember the right hand rule again, use your thumb for the current, and you have, okay, well, obviously it's coming, my fingers are coming out underneath and they're disappearing from the top. So what's important to note is that this is a magnetic field. Okay, so if you have a current that is flowing, you now have energy that is stored in the magnetic field. So unlike a capacitor, if we disconnect the voltage from a capacitor, disconnect the battery, what happens to the capacitor? We had a bunch of charges hooked up right here that are stuck. Those are stored in an electric field, right? What happens if we disconnect the battery? They stay there. They have nowhere to go. How about an inductor? Well, let's say that there's a magnetic field. The magnetic field that's floating around is carrying energy for us, and we suddenly stop the current. What's going to happen to that energy?
It's going to go away.
It
It
can't.
dissipates.
It can't. Energy can neither be created nor destroyed.
Destroyed or
It-
created.
It just has to change form. Well, it exists, right? So where's it going to go? What it's going to attempt to do is it's going to attempt to find some way to get rid of itself. You know, if you just left it there, eventually it would succeed in, eventually dissipating somehow. What really happens is that magnetic field now, our current was initially flowing this way to the left, right? Well, we think about it, we have a plus terminal and a minus terminal. In order to get that current to flow, it goes from plus to minus. But now we're left with nothing. We just have this magnetic field. What it attempts to do, it generates a voltage right here in an attempt to get current to flow that way. And this voltage will get bigger and bigger and bigger until it finds a way to get rid of itself. And how does it find a way to get rid of itself? If it gets a big plus voltage on this end and a big negative voltage on this end, if this isn't hooked up to anything, what's eventually going to happen?
Go to ground.
Well, if there's ground, but if it's just in space, eventually it's going to find a way. And what is that known as? These terminals are eventually going to figure out how to find each other.
Is that an arc?
That's an arc. Yeah. So the voltages will get big enough that eventually that power, that energy finds a way to dissipate itself in the form of a spark.
Where does that extra voltage that builds up and builds up and builds up until you create an arc, where does that voltage come from?
It comes from the fact that there is this magnetic field energy that exists.
So this is for the AC currents, right?
This is for any current. This is just how an inductor works. If you basically have magnetic field energy, it has to go somewhere.
Why can't it just sit there?
Where's
Like a capacitor?
Because magnetic fields don't behave like that. No one's ever figured out a way to save a magnetic field energy.
Okay.
It just it just by nature does not work that way. So the energy has to be dissipated somehow. So in that regard, capacitors and inductors are very, very different beasts. Now, does anybody ever seen an ignition coil?
Yep.
Okay. So if you've seen an ignition coil, what you basically do is you establish a current flowing through it, and then you suddenly break it.
Gives you a spark.
Which generates a very high voltage. In this particular case, what you do is you have a plus and a minus terminal that are designed to basically control a spark. And because that voltage is really, really high, then you can get a really, really good spark by determining how far apart these electrodes are. That determines the breakdown voltage that is necessary for that spark to occur.
Spark plug's the same thing.
That's exactly right.
About 40,000 volts.
Yep.
So the coil on a car is just a big inductor.
Yep. That's why we call it a coil, because it's literally a coil of wire.
But we light the beacon lights on the antennas.
Mm-hmm.
There are two coils interconnect without touching each other, so they prevent the lightning to strike. And the voltage just jumps over inductive and it's the bolts.
There you go. Okay, so now what we're going to do is we're going to go back to our book. And okay, what electrical component is typically constructed as a coil of wire? That's an inductor. The type of component that stores energy in a magnetic field is an inductor. And the ability of inductor to store energy in a magnetic field is inductance. And the unit of inductance is a Henry. Okay, so now what we're going to do is we're going to talk about batteries really quickly. And then I believe we're talking about semiconductors. But you know what we're going to do first? We're going to talk about the fact that inductors and capacitors behave in certain ways. So what have we looked at so far? We hooked up our inductor and our capacitor to what?
Batteries.
A battery. Okay, and what is a battery? AC or DC?
DC.
DC, okay. Now, so we know that if you hook up a capacitor to DC, what will happen? Initially, the thing is uncharged, right? So you'll have a lot of current flowing into it. What'll happen when the capacitor cannot hold any more charge?
Current stops flowing.
The current stops flowing because current is movement of electrons. If it's full, you can't put any more in it. So if you have the same thing in this situation, we make an inductor like this. And that's DC. What happens to the inductor? What is the inductor really? What is it made of?
Coil of wire.
Coil of wire.
Coils.
Okay. Wire is what? Wire is a conductor or an insulator?
Conductor.
An inductor. So sure, it makes a magnetic field, but really it's just a piece of wire, right? And a piece of wire is a conductor. So what's going to happen here is we're going to get a current, and what's going to happen to the current?
It's just gonna keep flowing.
Just going to keep going. Yeah. So for DC, what does an inductor look like? It looks like a short circuit because it's just a piece of wire. Okay, so what does a capacitor look like up top once it's charged up?
An open circuit.
It looks like an open circuit because what is a device called that can accept no current? If you think about it like that, that's basically a resistor with infinite resistance. There is, once it's charged up, these things are completely equal. Once it's charged up, these are completely equal. So an inductor at DC looks like a short circuit. A capacitor at DC looks like an open circuit once it's charged. So now we're going to play a game with this. We're going to take our happy currents, our happy batteries, and we're going to replace them. You know, everything is steady state with DC. Once it's doing something, it just stays there. But now we're going to take our batteries and we're going to replace them with that.
AC.
And we're going to replace them with AC. Okay, so now we have AC, which is in the green circuit, the green color. Okay, so now we're going to take our AC and we're going to take at first the positive side of the wave. So the first thing we're going to do is look at the positive side of the wave. We're going to have a positive and a negative and a positive and a negative. So when it's positive, what's going to happen to the capacitor? We'll start putting positive charges up here, right? Pulling the electrons away, and they'll show up down here. So what's going to happen to the inductor if we just have a positive current? It's going to flow this way. Okay. While it's doing that, when current is flowing, what does it make internally? It's going to be storing energy in what form? Magnetic field. And by holding up your hand and it's flowing down, the magnetic field is going to be going into the page over here and out of the page over here. Like that. Okay. Now, our next thing is, what are we going to do? We're going to transition to the negative side. Uh-oh. Well, so now we get to reverse our battery. Our battery, this becomes the minus and this becomes the positive. We're going to do the same thing on this one. Okay, so let's say we now hook up our battery. And we have all these, we'll look at the capacitor up top. We have all those positive charges. What are they now going to experience? What does the battery look like? They're going to be all called home because the positive charges now see, oh, there's a negative terminal over there. I better flow back. And then the negative charges at the bottom are going to see a positive terminal, and then they're going to flow back. So eventually we'll get nothing. But if we leave it there long enough, what's going to happen?
It's gonna switch back.
We get positives down here and negatives up here.
Yeah.
So in other words, what ends up happening is we get current flow. So if we have a capacitor at AC and we always get current flow, what does that look like as far as the battery is concerned? If there's always current flow. What thing allows current to flow all the time?
Resist.
Nope.
Short
Short
circuit.
circuit.
Yeah.
Yeah, a short circuit. So for AC, a capacitor
Oh,
looks like
okay.
this. For AC, a capacitor looks like a short circuit. For DC, a capacitor looks like an open circuit. So now, anybody have any guess what's going to happen when we go to the inductor? So we're going to take our inductor and we're going to flip. We just flipped the current, right? We flipped the voltage. And what did we say happens to an inductor that has a magnetic field around it? As soon as you pull away the battery, what does it try to do?
Arc.
It tries to arc. It tries to flow current in the opposite direction. Except now you're intentionally changing the direction of current. You're actually not even taking the battery off. You're saying, I'm not only just taking the battery off, but I'm flowing opposite. I actually flipped it. I even went further than that. So what's going to happen to that magnetic field energy? It's going to fight it, right? So it's going to fight switching to the other direction. Well, if it's going to fight switching to the other direction, that means fundamentally, you're going to have a really hard time stuffing current into it, stuffing voltage into it and getting a current to flow, because it's always fighting you. It's always fighting back. Because of that, you are going to get an open circuit, because if it's always fighting back, you're going to have a really hard time getting current to flow, which means that you will get this. Okay, this is really actually very, very important and profound, because what it means is that for a capacitor, at AC, a capacitor looks like a short circuit. For a capacitor at DC, it looks like an open circuit. For an inductor at AC, it looks like an open circuit. And for an inductor at DC, it looks like a short circuit. And why are these so profound? Because each of them acts opposite of the other one. So now, if I were to do this, for instance, I'm going to draw a voltage source, which actually, this is going to be a complex voltage source. And I'm going to do this. And I'm going to do this. Okay. So I'm going to say that this voltage source is an AC voltage. But added to that, I'm actually going to say that I'm not just going to make it an AC voltage. I'm going to add a DC voltage to it so that my zero line is right here. Does everybody understand what I just did?
Nope.
Not even close.
Okay. What is this voltage? right here.
That's AC.
Okay. And what is my horizontal line? If it goes from positive to minus, what voltage is my horizontal line?
Zero.
0. Okay, now I'm going to take this and I'm going to, let's say I have an AC power supply right here, but below it, I have a battery. What will that do? Those will actually add my voltages together. So let's say that this is let's say that's 120 volts AC. That's going to look like this. And this is 200 volts DC.
So you can add AC and DC power in the same circuit?
Oh yeah. We do this all the time. It's actually really important. So when this goes up to its peak, remember what its peak voltage is?
170.
170 and minus 170. If I were to add those two voltages together, what would the highest voltage that I ever got be?
370.
I'd have 370. And what would the lowest voltage be?
30.
30. Well, it would look like this.
Where does the 30 come from?
Well, it's 100, it's 200 because that's my DC voltage, and I have a minus 170. So 200 minus 170 gives me 30. So I would basically just have an AC voltage that is now offset. It's shifted. But let's say that I'm looking at this from the outside world. I just see this voltage right here. It's ripply, it's bouncing up and down, but does it ever go negative? Ever?
No.
No,
your
it doesn't.
Your DC is your insurance, right?
That's right. That's right. So I have AC and DC and they're superimposed with each other. This is called superposition. So this is my interesting voltage source. Okay, but now, true or false, there really is AC in there and there really is DC in there.
You just told Max that's how it is.
That's right.
Max and I are struggling to believe you.
They are really both there. Okay. And what did we just determine? What did we just say that a capacitor looks like? At AC, a capacitor looks like a short circuit. For DC, a capacitor looks like
An open circuit.
open circuit. How about the inductor? For
It's the opposite.
Yeah, AC, it's an open circuit. And for DC, it's a
Short circuit.
short circuit. Okay, considering that I have AC and DC components right here in my voltage, what's going to happen to the AC portion of it? Which way is it going to go?
Go through the inductor.
Well, no, it's going to go through the short circuit. So the AC component is going to pick the easiest route.
Okay, I see. Yeah. All right.
The AC is going to go this way. Which way is the DC going to go?
It's not.
Straight line.
It's open, right?
What have I just done?
Sounds like you split current without having a potentiometer, resistor, whatever.
Oh, no, I did more than that. I separated my AC and my DC stuff. So what's my voltage going to be over here on the side where the DC is? If I were to take a measurement, what am I going to see?
200.
200 volts DC. How about over here on the AC side?
120.
I'm going to separate those. Could I, if I had power supplies, could I run this thing backwards so that I
Yes.
actually generated this weird looking voltage? I
Sure.
could. Yeah. Okay. This is known as a filter. Capacitors and inductors are the basis of something called filtering. We use filtering everywhere. And this, because capacitors and inductors behave differently between AC and DC, this gives us an enormous amount of power. The ability of a device to resist the flow of AC is known as impedance because they already used resistance. That is known as impedance. And another version of that is called reactance, which we're going to get to.
Can you go over the yellow color again?
Yeah, is it
Ju-
too
ju-
kind of hard to
Just
see?
one more time.
Okay. So let's say that I have, again, right here, the key is that I have AC and DC right here, right?
Yep.
AC is this and DC is this. So if I just look at the AC, the AC is going to pick the easiest route to flow. So my AC, it's either going to go through an open circuit or a short circuit. Which way would you say is the easier route to follow?
Open circuit.
Remember, an open circuit's an open circuit. It doesn't go through. It's open. It's two terminals with a space. So my AC is going to go which way?
Short
Through
circuit.
the short
Short
circuit.
circuit.
Oh,
AC
okay.
is going to go this way.
Got it. Okay.
And the
Thank-
DC is going to experience either a short circuit or an open circuit. So which way is it going to go?
It's going to go through the short circuit. Okay.
Yep. So the
Thank
DC
you.
goes this way. And this is how we separate AC and DC voltages. And it's a good thing that we do this. And we're going to get to exactly why very, very shortly. So,
Okay. Thank you.
yep. Okay. So those are how those are how capacitors and inductors behave at the extreme. So if you want to think about it, the AC that we did, we might as well assume that it's an infinite frequency. The DC, what frequency would you say that has?
It doesn't have a frequency.
Well, it's actually zero. It's zero frequency. So it basically becomes zero. Instead of, going up and down very slowly, eventually it just stops going up and down. So ZC is like zero frequency. Okay, so that being said, the next thing we're going to do is we're going to cover batteries. And we're going to come back to those, right? We're going to come back to capacitors and inductors because they're really interesting. So a battery is a way to store DC current, DC voltage. Battery chemistry, essentially, what did we say about energy? It can neither be created nor destroyed, right? A battery is a chemical energy storage device. You basically have a chemistry, which is a couple of different things. Lithium ion, everyone has a computer, everyone has a phone now. Lithium ion battery is what runs it. So if you have a lithium ion battery, it's got lithium metal and it has some other component in there that allows electrical interchange, interchange of electrons, and allows them to flow through something. That is a reversible or rechargeable battery, and it's a good thing. Otherwise, once your phone was dead, you just pull out the battery and toss it out in the trash and get a new one. So a carbon zinc battery is not rechargeable. That's your standard old school battery, like a D cell that is a non-rechargeable battery. An alkaline battery is also non-rechargeable. A lithium metal battery, has anyone ever seen one of those? I'm guessing you probably have. Where do you find a lithium metal battery? Lithium metal battery, does anyone have a watch that has a button cell in it? A lithium button cell that lasts for 10 years?
Smoke detector.
Yep, smoke detector batteries. Those are single-use batteries. They're known as primary cells. They're lithium, but they basically, once you're done with it, it's dead. But they last for a really long time. Then there's also a rechargeable battery. So nickel metal hydride, that's about a 30-year-old technology that still works really well. Lithium ion, those are used in cell phones and many other devices like laptops. And then a lead acid battery. that's about 150-year-old technology that we still use in cars. So those are all reversible and thus rechargeable batteries. Okay, so now we're into diodes. So remember we said that there's conductors and there's insulators, or there's things that are dielectrics and stuff like that. Well, okay, so we know that there are things called conductors. What's an important characteristic of a conductor? What does a conductor do?
Stores
Tracks.
energy.
Oh, it
Passes.
allows what to move very easily.
Passes it through, it conducts it.
Passes electrons. Okay, an insulator.
Stops the electrons.
Yep. So electrons are not easy to flow through an insulator. Okay, now, so there is something called, it's halfway in between the two.
Diode.
A semiconductor. A semiconductor is a material that can operate as a conductor, but it can also not operate as a conductor very well. So depending on how how it's made and what it is, and typically what material you pick. So some semiconductor materials are silicon and germanium. Those are really, really popular. Oh, arsenic. Those are semiconductors. They're typically, so in an atom, the outer shell of an atom typically is going to have 8 electrons to fill the outer shell. If you have 3 or 4 or 5 in it, it's kind of halfway in between having a few extra, having a few out there and having a whole bunch out there, because it typically will have between 1 and 8. Well, so these are kind of in between. And because they're in between, they're not really conductors, and they're not really not conductors either. So the most popular one is silicon, because there's a ton of it on Earth. We find it in glass as silicon dioxide. So we find it in sand. We find it, it's all over the planet. So there's tons and tons of silicon out there. And silicon has 4 electrons in its outer shell. So it's really right in the middle as far as, between 1 and 8. So silicon is, well, it's kind of shiny and kind of metallic, but sort of not. So, I mean, it really fits the bill. If you try to pass current through silicon, it probably won't go very well. If I put a plus here and a minus here, it's probably not going to do very much. Now, there is something that you can do to get this to work better. And that is, you have this silicon here. And what I'm going to do is I'm going to throw some other material in the silicon, just a little bit. And I'm going to add something that is missing a few electrons. And we typically use something like phosphorus. And since it's missing electrons, we're going to call this a P for positive. And I can take another piece of silicon and I can throw in something that has a couple of extra electrons. This is known as doping of the material. And it's a little more negative because the electrons are negative. And that becomes an N. Well, if I do that and I hook up a battery to it, what will happen is, as I increase my battery voltage beyond a certain point, it will overcome silicon's innate desire to not do anything with electrons. And above a certain voltage, it will actually allow current to flow. If I reverse the voltage or go down to 0, basically it becomes a brick wall. So for silicon, above 0.7 volts, this is its turn on voltage, it will allow current to flow. Its schematic symbol is that. So it has a plus and a minus. This is the anode. This is the cathode. if I were to see one physically, it would look like this with a black band on it. This is the plus terminal. This is the minus terminal. What's cool about a diode is that, once again, above a certain voltage, what is it allowed to do?
Allows current to flow.
Allows current to flow. Below that voltage or in the opposite direction, what does it do?
Nothing.
Nothing. Essentially, this is a
Blocks it.
one-way street device. That is a really cool device because here's the use of our one-way street device. Let's say we have a voltage that does this. Okay, we have our plus side and our minus side. And we take our battery voltage that looks like that, and we hook it up through this. This is our diode right here. It has a plus and a minus. So what we're going to do is go through this voltage, and we're going to say that this is 0.7 volts, that dotted line. Okay, we start at 0. Does current flow through the diode when we're all the way at 0?
No.
Nope.
Nope. Okay. When does it start to flow? At what voltage?
0.7.
Yep. And if this peaks at, let's say, 12 volts, and we go down to minus 12 volts, where does it flow? Where does it start? Where does it turn off again as we progress to the right?
When it crosses the line.
When it crosses below the line. Okay. So that becomes a zone where it doesn't work anymore. So now this stuff down below the line disappears. It's gone. What does that look like? Does the voltage ever go below? Does the current ever flow when the voltage is below 0?
No.
No.
Does it ever reverse direction of flow?
No.
Nope. What is it called when something never, when current only ever flows in one direction? That has a name.
It's called DC.
That is called DC. What have we done with our diode? We have taken a voltage that was
DC,
AC,
turned it into DC.
and we just made DC out of it. Why is that important?
To recharge all the devices.
So you can run any DC powered device like a computer. Yeah. So basically what the semiconductor allowed us to do in this form is turn AC voltages into DC voltages. Incredibly powerful. So here's the next portion of semiconductors. Well,
So
let's
that's
say
the big brick in my power line to my computer.
Yep.
Is splitting the AC coming out of the wall and cutting it basically in half, making it DC, and that's what feeds into the computer out of the other side of the big brick.
well, let's say that if you were to take this looking voltage and stick it into your computer would be really pissed off. But we're getting to that. That's coming up next.
Okay.
So
Okay.
Scott,
Yes.
if you're talking about this function as something that converts AC voltage into DC function, DC voltage, are you talking about a rectifier?
Yep. That's a half-wave rectifier.
Okay.
Okay. So now let us take let us take, because remember we had a P and an N before with a diode, but now we can do a PNP. Well, if we have, this is now 3 terminals. And sometimes this is drawn like this, P, N, P. Now, could you also do NPN? Just so long as
Yes.
they're different, sure. And if you were to have now 3 terminals, what would happen is, if we look at this, from P to N, what is this portion? We just drew it on the left.
Diode.
A diode. Okay. And then this opens up above 0.7 of a volt. Well, it just so happens that if there happens to be a source of power up here, when that opens up, when that PN opens up, you get a flood going the long way from the top to the bottom as well. This has a name,
Resistor.
a transistor. It's an electrically controlled switch where basically if you turn on this first diode right here, you get a flood coming down through the entire device. So a small number of electrons over here that turns it on creates the ability to pass a huge number of electrons on the right-hand side, which is
So a
great.
dumb question here, Scott.
Yep.
What does the N stand for?
N is negative. It's
Oh.
it's an area that's been doped with a few extra electrons.
I told you that was a dumb question.
Yeah, okay. No, it's okay. So now let me ask this question. If we were to take a look at this one right here, which way would the current have to flow? From the top to the bottom or the bottom to the top? Thinking about how that PN works.
From the bottom up.
Bottom to the top. But it basically functions the same way. It goes from the bottom to the top.
And that's because it has to go through the positive before the negative?
Yep,
Is that correct?
Because it's still just a diode. The first part of it is still just a diode. And in particular, this kind of transistor, both of them, these are known as bipolar junction transistors, or BJT. And they have 3 terminals, which are called, and I'm going to draw this with the schematic symbol. These are called the collector, the emitter, and the base. So you have between the base and the emitter, you have to develop a voltage enough to run to run that diode forward. So if it's a silicon transistor, how much voltage is required to get it to go?
0.7.
0.7 volts for silicon. If it's germanium,
0.3.
it's 0.3. Yep. Those are just intrinsic properties of the material. So these are 2 different kinds of transistors and diodes. The forward drop of a silicon diode is 0.7. For a germanium diode, it's 0.3. But they can both be used the same way. And what's cool about it is that once you have this, if you have a little bit of flow of current from the base to the emitter, you can get 200 times as much current flowing from the collector to the emitter. This gain, as it's called, and how do we often measure gain? In decibels, right? This is actually known as the beta of the transistor. That gain in this case is known as the beta, and that can be up to 200 times. So when you look at a transistor data in the data book, you'll see that there's a beta listed for the transistor, and that's current gain.
And where does that current gain come from?
That current gain comes from the fact that if you think about it, this is really 2 separate things. You've got a diode, and then you've basically got this other path which goes this way. And because you've now opened up this diode, the diode is now connected to this other source as well. And you basically, because of how it's built, you develop an enormous flood. This actually was developed in the late 1940s at Bell Labs.
Don't bring the vacuum cleaner down.
I won't, promise.
I'm not vacuuming either.
Okay, so this is known as a transistor. This in particular is a bipolar junction transistor, and it has 3 terminals: the base, the collector, and the emitter. Now I can draw another version of this, which looks like this, because that is a current device. There are many different variations of this. What do you all notice looks like is right there?
Capacitor.
That's a capacitor, isn't it? How does a capacitor work? What kind of field?
Electrical.
Magnetic.
A capacitor Yep, it has, you
It's
develop
electric.
electric field. You have electric field forming right there. Okay, this is known as, oddly enough, a FET or a field effect transistor. By applying a voltage right here at the gate, that's the name of the terminal, it's a gate. And these are very often interchangeable. There's two other terminals. There's a source and a drain. The source is the source of stuff and the drain is where it all goes.
So do we have to have an electrician license to be a ham operator?
No,
Oh, okay.
no, this is semiconductor fit. This is all semiconductors. It's on circuit boards. You can build anything you want.
Yeah, I've done some soldering on those, but
Yeah, I
no,
used to work on them too, long time ago.
yeah, a long time ago.
Okay, so this is a field effect transistor, and it's called a field effect because there's an electric field that's running the thing. So let me ask this question. How much current flows into the gate, looking at how it's built? Think hard about this. Once it charges up that little capacitor, what's the current?
9 volts?
No, what's the current? If
Oh,
it,
the
if
current.
it's a capacitor and it charges up, how
It's
much
already
more
charged
can you
it
stuff
up.
into it?
None.
None.
Nothing stops. It's
These
full.
are super efficient low current devices. Because if you just simply apply a voltage there, you get a current flow from the source to the drain. It opens up the channel. So if I had a choice of building a really energy efficient system, would I use a FET or a BJT?
Probably a fit.
I'd use a FET. These are way more efficient. The FET is way more efficient. This FETs is actually how most of our electronic devices are built today. They're really easy to build on on printed circuit boards, on semiconductors. You know, if you're talking about sending out a chip, a wafer to have a billion transistors put on it, they're typically going to be some variation of that.
So tell me again, what is a FET and a BJT?
Field
Field, okay,
effect
okay.
transistor. And this is a bipolar
Okay, thank you.
junction transistor. Okay, so now we're actually going to figure out how to use these things. Like, why would we bother to do this? Well, what's the point of all this? Okay, so now diodes, again, a diode has an anode and a cathode. It's a one-way street. The cathode, this is really important. The cathode is marked with a stripe. What is the forward voltage drop of a diode? In a silicon diode, how many volts is it again?
0.7.
0.7. And in a germanium diode, it's 0.3.
0.3.
Yep. Okay, a special kind of diode, instead of just passing current, it does this. This is called a light emitting diode or an LED. We use them for lighting now, a lot of it. An LED is also used as a visual indicator. Okay, transistors. Which component can be used as an electronic switch? That's a transistor. The device's ability to amplify a signal is known as its gain. A transistor is the device that can provide power gain. Again, there's that letter beta that determines how much gain it has. 3 regions of semiconductor material is a transistor. Bipolar junction transistor has an emitter, a base, and a collector. Now, you'll notice when you start looking at a lot of these questions, some of these answers don't make a lot of sense. So, you know, with any multiple choice answer like this, two out of the 4 answers aren't going to make a lot of sense. So you can filter out the 2 that are really kind of dumb in the first place. That makes it a lot easier. So if there's something you don't really remember, you can always just knock out 2 of them as being silly. An FET, what does it stand for again?
Field effect transistor.
Field effect transistor, and it has a gate, drain, and source. Okay, so now we are into schematics. The name of an electrical wiring diagram that uses standard symbols is a schematic. What is represented in an electrical schematic? That is component connections, not physically how they're laid out on the board, not how they're wired together, but how they are electrically connected. Okay, so the first thing I'm going to ask, if you know the answer, just tell me what it is. Element number 1, what is that?
Resistor,
Resistor. How about element number 2?
transistor,
What kind of transistor?
NPN,
It's a, well, yes. but what
bipolar,
bipolar junction transistor. And in particular, that is an NPN. The way to remember that it's NPN, because a PNP will have the arrow pointing in. The NPN transistor, you'll see, you notice the arrow coming out of it?
Yeah,
Would you say the arrow is not pointing in?
it's going to ground.
Right, but
Pointing out.
would you say that it's not pointing in?
Yes.
Negative.
N, not, P, pointing, N, in. Not pointing
Pointing
in.
north.
Right. Well, you could, yeah. But that's the way I've always remembered an NPN transistor, because the arrow is not pointing in, NPN. Item number 3
Lamp,
Little lamp,
is a little lamp. Yep. Number 4.
battery,
Battery.
Yep. And how about number 5? We haven't really talked about that one.
ground.
That's a
is that a
ground.
ground?
Yep, a ground. Notice it shows up in 3 different places, doesn't it?
Mhm.
Well, ground is our 0 voltage reference point. That being said, what can you say about those 3 different points? They're shown for convenience, but in reality, they are all the same. Ground is ground. It's our 0 volt reference. So if I were to draw my ground bus, it would look like this. I would know that actually I had this and this and this all connected together. This is my 0 volt reference for the whole thing.
Mhm.
Okay, now notice that we have a voltage source over here on the left-hand side. And there's also a battery on the right-hand side. How does that work? What does the voltage on the left-hand side do? What's its only function?
Current.
To switch the transistor on and off.
Turn the transistor on and off. That's right. It basically does this. It runs this transistor and runs it forward. So why do you think this resistor is here?
To limit the current going into the transistor.
Right, because once the transistor turns on, it's on. If we don't put a resistor there, we're going to end up letting all the smoke out of the transistor, and it's going to end up in a little black charred mess. So by putting a resistor there, we limit the amount of current that can flow into the transistor. Because remember, DC, when it hits a resistor, it's going to limit the current. Okay, but now once we've established that we have the left-hand side, now we have the right-hand side. So we have a voltage source over here at number 4, which puts current through the light. And once the transistor is turned on, the current flows through the transistor, and we get current flow through the light, which turns the light bulb on. So basically, what does this thing do? When we put a voltage over here, it makes the light come on. That's a very simple switch. And this is actually operating in what we know, what's called saturation. And we're going to get to that very shortly as to what saturation mode is versus linear mode versus cutoff. Okay, so now we come back to here. we killed that one. You guys did a fantastic job on it. Okay, so now we're going to do this next one. Okay, everybody see that? Everyone see the diagram okay? Okay, good. This is our voltage source on the left-hand side. I'm going to turn on my annotation again. Draw. Okay, so this is my voltage source on the left-hand side. And by looking at that, plug, what's it gonna be? AC or DC?
AC.
AC.
That's gonna be AC, yeah. And the reason that it's AC is because they drew it like a power plug. So, it's actually gonna be this.
It's like an outlet, right?
It looks like an electrical outlet. Okay, which means that it's going to go plus and minus, right? We're gonna get rid of that. It's gonna go plus and minus. Agreed?
Yep.
Agreed.
Okay,
Agreed,
Okay.
although the transformer at 4 kind of gives you a clue that it's going to be AC anyway.
we're getting to that. Okay, because we got to talk about transformers and we haven't done that yet. Okay, item number 2. Every
fuse.
circuit that you build should have what in it?
Fuse.
Fuse.
A fuse, yep. And what's the purpose of a fuse?
Safety.
Prevent-
So you don't burn the house down.
So you don't burn the house down. This is for safety. Yep. So it prevents an overcurrent. It prevents an overcurrent condition or a current overload. How about number 3?
A
Single
pole, single.
Right? That's actually a single pole, single throw switch. And the reason that we call it that is because a pole is a number of a pole is a circuit that is turned on and off. A throw is the number of directions that it can be made to connect to. So if I were to draw, let's say, another position here, like right there, that the switch could be taken to, that would be a single pole. It would still be one pole because it's only one circuit, but that would be a second
double
throw.
switch.
That would be an SPDT switch, which is a single pole, but now a double throw. In other words, I could turn it to the off position, or I could turn it to one position or another position. So that's how switches are defined. The number of poles. So if I were to draw a switch that looked like this, for instance, right, and I had a second one that was ganged together that went like this, and I were to draw a line right here and a line right here, and I showed these being connected together,
Right.
Double switch.
that would be a double pole because it's 2 separate circuits. And because each of them could be thrown to 2 different positions, it's called a double pole, double throw. And that's how we get those names. Okay, so now we are into item number 4. Item number 4 we haven't talked about, but it's really important.
Transformer.
It's a transformer, but what is this right here on the left-hand side? That should look familiar because we've
Coil.
talked about it. That's an inductor, isn't it? That's an inductor, right? So now that we have an inductor there, what do we know an inductor makes?
Magnetic field.
Magnetic field. Yeah. Okay. So instead of having a straight wire, we now have a coily wire, right? If we have a straight wire, the magnetic field looks like this around it. But if we have a coily wire, the magnetic field actually looks like this. And it has loops around the outside. It loops back. This is known as a solenoid. And the magnetic field goes through the center and it kind of connects around the outside, and we can draw more magnetic field lines. You may have seen something that looks like this before. So you have basically the magnetic field is concentrated on the inside. If you've ever seen like at a junkyard and they have a big magnetic thing that picks up like an entire car body at a time. That's basically what this is. It's a coil of wire. Now, in order to intensify the magnetic field inside there, you can actually make some modifications to it. I can take my coil, it looks like this, and I can wrap my coil around a piece of iron or steel. And if I do that, let's just say that I make it in this shape. What will happen is that iron and steel, anything that's a ferromagnetic material, something that can be made into a magnet, has something called a higher permittivity. And that permittivity, and it's an intrinsic property of the material itself, will be able to concentrate a magnetic field inside it. Now, the interesting thing is, if I were to do this material, if I've chosen it properly and I've made all my connections, notice it's in the shape of a loop. What will happen here is that my magnetic field will not only pass through like this, but it will actually be channeled really well through the core in a magnetic circuit around the core. So if a current makes a magnetic field, what does a magnetic field make? And again, this only works for AC. If a current makes a magnetic field, what will a magnetic field make? What do you think?
Current?
It'll make a current. Yep. Energy can neither be created nor destroyed. So if I have two coils wrapped around a single core, the core constrains the magnetic field. This is known as the primary side. This is known as the secondary side, or primary winding and secondary winding. And what it allows me to do is couple two coils together using something called mutual inductance, and take energy on this side and move it to energy on this side. Now, the really cool thing about this thing, which is called a transformer, is that a transformer allows you to literally transform one thing into another. I can pick the number of turns to wrap around that part in that coil, and a number of turns to wrap around this side. What I will get is that my voltage ratio using AC will be proportional to the number of turns that I wrapped around it. So if I, for instance, used 100 turns on this side, and I only used 10 turns on this side, what is my ratio?
10 to 1.
10 to 1. That's right. If I were to put 120 volts AC over here, what would I get out on the other side?
12.
I'd get 12 volts AC. The frequency would be the same, but what I have done is, by wrapping this thing with coils of wire, I have transformed, literally, that's why it's called a transformer, my voltage from one voltage to another. Now, what we're going to do next is we're going to take this and we're going to say, if I were to take, let's say, hook up a device that drew 10 amps, a current of 10 amps, what would my power be over here on the right-hand side?
120 watts.
120 watts, because power is equal to what?
IE.
I times E, which is equal to power equals 10 amps times 12 is 120. And that's in watts. Okay, now if I've built my transformer so that it's efficient, if I have 120 watts on the right-hand side and I have 100% efficiency, how much power would I need on the left-hand side? How many watts?
10.
No, if I use 120 watts on the right side, how much power do I have to put in on the left?
120.
120 watts. So I know, again, P is equal to I times E. Equals in this case, 120 watts, because we know that. Right? We know that we want it to be 120 watts equals I. We don't know what the I is, but we know that our voltage is 120 volts. So therefore, our current is 1 amp by Ohm's law. So our current is 1 amp on the primary side, and our voltage is 120 volts. And on the secondary side, our current is 10 amps and our voltage is 12 volts because the power has to be equal. So now what's really interesting about this is I could also take this transformer and say, okay, what is my resistance of this thing that is using 10 amps at 12 volts? E equals I times R. Does everyone agree with that? Ohm's law again?
Mhm.
Okay, so 12 equals 10 times R. So what is my resistance equal to? 1.2 ohms. Right? Does everybody see that? Understand why? It's just Ohm's law. Okay. And now I'm going to do the same thing over here. I'm going to use the same exact formula. E equals I times R. Right? Ohm's law is Ohm's law. We can't change it. What's our voltage on the left-hand side?
120.
120 is equal to 1 amp times R. This is magic. What is my resistance?
120 ohms.
120 ohms. What was the resistance on the right-hand side?
1.2.
So what did the resistance go up by a factor of?
100.
100, which is the turns ratio squared. So if I had something that was 10 ohms on the right-hand side, what would it be on the left-hand side? It would be 1,000. I could also use this back in reverse. I could make my turns ratio backwards, and that's known as an impedance transformer. We use that for audio circuits and all other kinds of stuff like that. We also use this for feeding antennas. So if you have a very high impedance, you can transform it down. If you have a very low impedance, you can transform it up. So transformers are an incredibly powerful tool. So item 4 is a transformer. Item 5, what's item 5 there?
Diode.
That's a diode. What does the diode do? What does diode do?
It's one way.
It takes an AC, because we have AC over here, and which part of it does it allow to go through?
Positive.
The positive side. So only this over here. It blocks out all the stuff on the right. If we were to look at this, it goes like this, and a bump, and a bump, and a bump, and it knocks out the bottom part. If you knock out the bottom part, what do you have?
DC.
DC, but it's really kind of ugly, isn't it now? I mean, who wants to look at that? Blah, 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 blah. What happens to the capacitor down here at number 6? When the voltage goes up, what happens to the capacitor?
Charges.
It charges up. So you get pluses forming here. What happens when the voltage goes down at this point?
The capacitor feeds it.
The capacitor is already charged. So the capacitor then uses its charge and dumps it out. So now, instead of that ugly wave, we have something that looks like this, which is still a little ugly, right? But it's not as ugly. It doesn't look like this. It's definitely not as ugly. It's smoother. So item number 7, what's that?
Resistor.
Yep, and item number 8, this is a light emitting diode. Notice the light flying out of it. That's operating as a light, that's operating as a switch, saying that our power supply is working. So we also have item 9 right here. What is that?
Potentiometer.
Potentiometer that's used as a current limiting device. And what is item 10?
Senior diode.
That is a special kind of diode. Notice, remember we said that diodes always work this way? Well, if you have something that works in a certain way, somebody's gonna come up with some way to use it a different way. So they turned it backwards. And at some point, a diode, when you try to stuff energy into it in reverse, it will actually work. But depending on how you build it, it might blow up. But if you build it sturdy enough, then notice that letter Z looking thing, that's known as a Zener diode. Above a certain voltage, it says, okay, I'm going to allow a certain amount of voltage to go through and everything else is going to get dumped out. So if this is, let's say, a 5-volt Zener diode, it's going to allow everything on this waveform 5 volts and above to get flushed down the toilet. Which basically means we get this looking wave coming out. What does that look like?
Looks like
conductor.
DC.
That looks like nice, clean, ripple-free DC, doesn't it? That is a half-wave rectified power supply that can run your computer or charge your iPhone or run something on a USB voltage. So what we built here is a half-wave rectified power supply. We have actually just built a power supply.
So I guess the capacitor stabilizes the voltage as well.
Yep, the capacitor, when the voltage falls, it basically acts as a filter by cleaning things up. All right. Everybody ready for a 5-minute break? Because this next part's going to kind of blow your mind.
Yeah.
Okay. Everybody good so far?
Yeah.
All right. Are we all having fun?
Yep.
Okay,
Yeah.
good.
Yes.
Okay.
Hate to break it to you,
Yes.
put my dog to sleep, but I'm okay.
What kind of dog? Where's the dog?
He's right.
Aw. Dog's not good with electronics. That's okay. They
No.
don't need to. They don't need to know.
No, partially it's age. He's 14, so he
Yeah.
sleeps a lot anyways.
Yeah, okay.
Yeah,
All right.
it's
See you
nothing
guys in
personal.
5. See you guys in 5 minutes.
See you in 5.
All right, come on, sir. Sorry, I can't have you on my lap, so. That's fine.
All right, who's got questions? Because now we're going to get to the mind-blowing part, which isn't really mind. It's just fun.
Sorry, so. Oh. I'm in class. Shh.
Who you got on your lap?
Wasn't me. Anybody with any questions before we start up again?
No.
Not a one, huh? Okay.
Come here, you.
I can live with that.
Hey.
The dog or a cat?
That's my cat.
Can we get a close up of your cat?
Sure. Come here, Bo. Oh, stop. Stop.
You know what's great about cats? They'll do whatever they want.
That's right.
Here she is.
So I saw a thing about cats on Nova and how cats, basically what cats have come to be and why dogs are different than cats and vice versa. And what it really comes down to is a dog wants to please you. A cat, and they just really don't care.
She's my baby though, Scott.
Oh yeah.
My cats get mad at me because they're not allowed in this room because I've already got 2 missing keys on my laptop because of them.
I know, I had to buy a new computer because she tore my other one up.
Well, I've had the experience of having a cat lay down on something and send a bunch of Morse code.
Oh man.
You know, it's comfortable on top of the radio. And, you know, sometimes they just stand on they walk across your desk and send Morse code.
Yeah.
So,
And my 2 labs are outside because they're like 3-year-olds.
yeah,
You
well,
get on the
right.
phone, they want to pick the noisiest toy.
Well, right, because they never grow up. That's
No,
just who
they
they are.
don't.
That's just who they are.
I used to be a dog person until this past weekend, staying by my friends. 2 labs. Hyper is everything.
Yep.
I couldn't wait to come home to my cat.
All right, everybody ready to do this next thing?
Mm-hmm.
Okay, does everybody see this circuit right here? Such a simple circuit, right? Such a simple circuit.
Of course, it only has 4 parts.
It only has 4 things. Okay, so number 1 is an AC voltage source of
Right.
some unknown frequency. Number 2, and the item that's identical to it, to the right of it, what are those?
Are those variable
Capacitors.
capacitors?
They are variable capacitors. And item number 3,
A variable inductor?
variable inductor. And item number 4 we haven't done yet is an antenna.
Antenna.
Okay, so what I'm going to do is transition to here because we're actually going to spend some time on this. And the reason we're going to spend some time on this is because it's going to show us that certain things sort of don't really always do what we expect them to. And certain things, because of that, become very, very important. So this is our in, and this becomes our out. Okay, everybody ready for this?
Mm-hmm.
Okay, so we have capacitor, C1, C2, and L1, or we can just call it L because there's only one. There's only one thing. Okay, so now what I'm going to introduce, like I said, this is actually going to be a little bit mind-blowing, but we're just going to get over it, is this is a piece of wire. I'm going to draw a piece of wire. What does a wire have? What is an intrinsic property of a piece of wire?
Conductor.
Yep, and it has, because it's not perfect, it has a little resistance in it, right?
Yep.
Okay, if I take this wire and I do this with it, what does it become? That has
An
an
Inductor.
That's an inductor. Does the resistance go away?
No.
No. So it has a little bit of resistance to it. Would you agree that those behave differently? Would you say that the resistance and the inductance behave differently?
Yes.
Yes.
Okay. By definition, resistance is what? It's the opposition of flow to what? DC current. How about an inductor? That is something that only really comes up, right? Inductors respond to AC current and also to DC current, but since we're only talking about AC, so we're looking at something called Z in this case, which is impedance. And part of Z is this thing called reactance. Reactance is how something behaves in response to AC. So we have this R and our X. And this is really, really, really important. As it turns out, if I draw a different XY plane, my R axis is here. My X axis is up here. Is there if this is our positive and our negative, our positive and our negative. Has anyone ever heard of anything called negative resistance? And yes, it exists, but practically speaking, does anyone ever deal with something called negative resistance? It's a resistor. It's measured in ohms, 10 ohms, 20 ohms, right? We really can say.
I was going to say a 3-year-old.
Yeah. Well, we can say that we don't have anything to the left of that line. We only have positive resistance. But now we have this thing called reactance, which is X, and those go plus and minus. So let us say that these actually are perpendicular to each other because it's an XY plane. And let us say that I have a resistance of, let's say, 3 ohms. And I have a reactance, which is its ability to deal with AC of 4 ohms. I'll put it up there. What can I make out of these things if I put a dot right there where they intersect? What could I build? Could I make a triangle? Right? I could make a triangle, right? And this triangle is actually a very important and common triangle. By Pythagorean theorem, x squared plus y squared equals z squared. What is my actual distance of this dot right here from the origin?
5.
Yep, that's a 3, 4, 5 right triangle. This right here is my impedance. You know what? I'm going to change it to a different color. I don't like that color. I'm going to use red. That's my impedance. It has a magnitude of 5 ohms. But wait a minute. What was my resistance? How many ohms?
3.
3. And what is my reactance? Which is the vertical offset.
4.
Plus 4. Yeah. Well, okay. So my impedance is a part of a 3, 4, 5 triangle, and it's 5 ohms. What else do you notice about it?
Well, it's got your angles.
Yeah,
involved.
there's an angle involved. And in this case, if I look at my angles for a 3, 4, 5 triangle, if I remember right, this is about 53 degrees to make that triangle, to make it work right. So my impedance of that thing that has 3 ohms and plus, we're going to use this as the x-axis, and 4 ohms in the y-axis has an impedance of 5 ohms with an angle of 53 degrees. That is my letter Z. That is known as my impedance. And this is actually really, really important, because what this means is if I were to just measure what the impedance is using, some kind of meter, I might get that it's 5 ohms. What I didn't get was the fact that the impedance also had an angle of 53 degrees. So what I'm going to go with now is I'm going to change Ohm's law slightly. Somebody give me Ohm's law. Somebody who needs to practice, tell me Ohm's law.
E equals I times E.
E equals I times R, but I'm going to replace R with this complex, as it's called, impedance. I'm going to rewrite it as E equals I times Z. Right? So let's say that I have a current that is 1 amp. What is my new voltage? E is equal to I times 5 with an angle of 53 degrees. Well, so my I is 1 ohm, there's 1 amp. So what's 1 times 5?
5.
5. But then there's this angle thing, which we could break down into sines and cosines. We could figure out what they are. What is my angle there? Angle of 53 degrees. What does this mean? If I were to draw my current, it would look like this, for instance. How many degrees are in a circle?
360.
360. So if this is my current and it starts at angle 0 and this is angle 360 degrees, well, my voltage E now has this extra term of 53 degrees. What does that mean is going to happen to my voltage? It's going to go through at 0 and look like this. So not only is it multiplied by a certain factor, but it's also shifted. The phase of it is actually shifted. So my voltage, is my voltage ahead or behind the current?
Follows.
So let me think if I did that right. So this is an inductor. And the voltage is, let me just make sure I got it right. The voltage with an angle of 53 degrees. Yeah, so the voltage is actually ahead. So actually, if I were to draw this, it would have to be ahead of it. It would have to be there first. So it would be right here. Darn it. It would actually be here. It would actually get there first. If I were to draw it on the circle, I would find that my voltage, here's my current, my voltage as we go around the circle, my voltage is actually ahead of my current. So what it means is that the voltage is actually leading the current around the circle. As we travel around the circle, the voltage gets to a certain point, 53 degrees before the current does. So what this means is that the voltage and the current, because they're going through an inductor with some complex impedance that isn't all resistive, actually changes the phase of one with respect to the other. Well, what it also means is that I can do all kinds of cool stuff. So let me show this, that X of L, X is reactance. So if I draw that circle again, we have R and X. They're perpendicular to each other. XL is equal to 2 pi FL. And what is my F in this case?
Frequency.
Frequency. So what does that mean if my frequency changes? What happens to how far up and down I go? What happens to that? Yeah, the amplitude changes. So what happens now if I also have this one, which is XC, which is equal to -1 over 2 pi FC? Where does that F term appear in my denominator?
The bottom.
In the bottom, yeah. Which means that not only is it inverse, so it basically, if my frequency goes up, my inductor goes up. If my frequency goes up, my capacitive inductance, if I have a capacitor, goes down. It gets closer to the middle, but notice there's that minus term. So capacitive inductance is always on the south side. It's always negative. Inductive is always positive. Well, could I pick a place where I had, for two different components, let's say I have a capacitor and an inductor and two things in series. If we're looking at impedances and reactances, these add together. Could I pick a frequency and components for L and C where when I added them together, they would cancel each other out?
Resonance.
Yeah. So, okay. So I have for the capacitor XC plus XL. That's my X total. Well, this is -1 over 2 pi FC plus 2 pi FL. And if I could say, okay, well, let's find out where they equal each other and cancel each other out. That means that the result would be 0 because they're equal and opposite. So I get 2 pi 2 pi FL FC is equal to 1. And I end up with, if I solve for F, is 1 over 2 pi square root of LC. So I can pick my inductors and capacitors so that for a given frequency, my reactance is what? 0.
0.
This is known as resonance. So what are some useful things to do with resonance?
Tune an
Tune an
antenna.
antenna.
Tune an antenna. You can also make an oscillator. You put energy into something that has an inductor and a capacitor in series, and what do you get? You get a frequency, because if I were to draw a frequency chart to say, okay, how well does this pair of things respond to a certain set of frequencies? If I pick my inductor and my capacitor, I would find that at FC, my impedance would go like this. So what does that mean if I have 0 impedance right there? That means that if something is coming along with a certain frequency, depending on how this is built, how these two things interact, if it's at a certain frequency, it's going to pass. Other frequencies, if they come there, if they're away from it, let's say that it's way over here or way over here, what are they going to encounter?
Resistance.
Yeah, they're going to encounter a high impedance, and maybe I'll get a tiny little bit out, but basically nothing. So what this allows me to do is pick inductors and capacitors so that I can actually build a device that can look like this. If I look at frequency from 0 to infinity, it can look like this. Where this is the ability to pass something. If it's wide open, it allows those things to pass. So would you say those frequencies that are allowed to pass are high or low? If I start at 0 frequency and it goes up to infinity, this is the ability to pass. In other words, if that window is there, those low frequencies can go through and the high frequencies can't. This is called a low pass filter. If I were to build something that looked like this, what would that be?
High pass filter?
That would be a high pass filter. If I were to build something that used a combination of the two that looked like this, it allowed that window to go through. That would be a band of frequencies. What would that be called?
Band pass filter.
That would be a band pass filter. Now, I could also flip these upside down, and then it would look like this. And let me make sure I get this right. I want to erase that. Depending on how I wired it, it could look like this, where I allowed this and this and this and this, and this and this and this and this, but it took a big nosedive right here. So the opposite of it would be called a band reject filter. That has another name called a notch, because it looks like a notch has been taken out of it. And all of these are made possible by doing what? All I've done is creatively select what? What are these things right here?
Different values of capacitance and inductance.
Yep. Okay. So if I hook them up in parallel, they still behave that way. If I hook them up in series, they still behave that way. At resonance, this becomes basically an open road. So that's like a short circuit. At resonance, this becomes a do not enter. Depending on how I wire them. If they're in series or parallel, I can make them behave totally differently. The key is that if I have picked them such that frequency is 1/2 pi square root of LC, I have achieved resonance and they will behave that way. So if, for instance, I take a circuit that has a this and a this, that has a resonant frequency associated with it. If I were to take this and pump this back into a transistor like this, where I took the output and plugged it back into the input, what would that be called? That's called an oscillator. Basically, I'm taking the output frequency and putting it directly into the input frequency at a frequency that it is happy to operate on. In other words, an oscillator will make whatever frequency that it can make, but by selecting different frequencies, by selecting your components, you can basically build an oscillator that generates a given frequency. How about if I do that? What can I do to my frequency? If my frequency is 1/2 pi square root of LC. What does that do to my selectable frequency? This makes it variable, right? If it's variable, then this becomes variable. What does that do to my frequency? What can I do with it?
Make it go up and down.
Make it go up and down. This is known as a variable frequency oscillator, or a VFO. If I use that to control my frequency, I can now tune the frequency of my circuit. I can tune the oscillator frequency. This is the basis for tuning of every radio before about 1985. And now, once we have that, once we've established that, the question is, how do you do such a thing? Oh, I hope you can see that. I hope this comes back up. Yeah. What? Not going to show it? Oh, come on. I had it up a second ago. There we go. Okay. Can everybody see that?
Yep.
Okay. So this is a very simple device that's known as an antenna tuner. So what do you guys see in the middle?
Coil.
A big coil, but what's connected to the coil on the left-hand side?
There's capacitors and inductors there. The coil's an inductor and these ones on the left are capacitors.
Right, but what's connected to the coil? What do you see coming off the coil on the left-hand side?
It's a dial.
You see it, well, there's a whole bunch of wires coming off of it, right? And those wires connect to that switch on the left-hand side. That is a rotary switch that allows you to pick certain taps on the coil. So it's not it's a variable coil, but it's a tapped coil. It allows you to pick like 12 different values by shorting out pieces of the coil. Now on the left-hand side at the top and bottom, what have you got?
Variable capacitor.
Variable capacitors. Because what is a capacitor built out of? What is a capacitor? How do you make a capacitor?
2 plates.
Two plates,
separated.
and
Yeah.
you take 2 plates and you stick them next to each other. So what if you have 4 plates, 2 from one side and 2 from the other? Then you have twice the capacitance. Now, what if you take 2 metal plates and instead of doing it like that, you build this, where one plate is over here and the other plate has just a tiny little bit of overlap with it. How much capacitance do you get?
Twice as much.
Well, no, because they hardly overlap. What if I took a
Okay,
plate
well
and put
then.
it here and another one and put it there?
Oh, I'm
How-
sorry. Yeah.
How much capacitance would I get from that?
A lot
Very
more.
little.
No, you get nothing. It's because they're not lined up with each other.
Oh, I see.
How about if I took one like this and I move them closer together, but they're still not touching? The capacitance would be going up slightly. How about if I took one and did this with it so that they were overlapping a little? They're still separated, but they're overlapping now. They're actually able to know that each other is there. So my capacitance is going up. How about if I took them and made it so that this was here and the other one was almost touching, almost completely meshed with it? That would be a lot of capacitance because it's the size of the plates that are, able to know that the other one exists. Well, this device called an air variable capacitor, it uses air as the dielectric that fills the gap. And the top part of it actually rotates and can completely, by turning it, unmesh or completely mesh with the bottom plates. And by doing that, you can continually vary the capacitance. It's a continually variable air variable capacitor. And that is the basis for this. What this allows us to do is we have draw. Okay, so we have an impedance up here R and X, and this is something. We don't know exactly what it is. Right? All we know is that it has some value, R plus X. So this is our Z of our antenna. It's our magic box up here, number 4. Well, okay, now if we have a capacitor right here, what is the impedance and reactance of a capacitor look like? We have our R over here and our X over here. A capacitor is always going to be on this vertical negative line somewhere. Well, by changing the value, we can change where that happens to be. And then we have that in parallel with an inductor. And an inductor is always going to be on this vertical line. And then we have it in series with another capacitor, which is always going to be down here. So by adjusting these components, we can take this and mess with it by putting them in series and parallel so that we essentially can transform our impedance from this to something that looks like 50 ohms resistive, so that it would hopefully just be resistance of 50 ohms. Sometimes we might get some inductance in there as well, or some capacitance, but ideally our transmitter is looking for 50 ohms purely resistive. By using these components, we can basically try to null out the reactance component, which is up and down. And curiously enough, if you've done that, it works in both directions. So that if your transmitter can put power out, then your antenna can put power into your radio to receive it. So this is an incredibly powerful device known as an antenna tuner. And this allows us to use an antenna that presents some unknown impedance to our equipment and make it look like something that we can actually use just by using those little devices. 2 inductors and 2 capacitors and an inductor. Yep. I thought I heard somebody say something. Nope. Okay. All right. Here we go. Resonant and tuned circuits. Which of the following is a resonant or tuned circuit? Inductor and capacitor in series or in parallel. Which of the following is combined with an inductor to make a resonant circuit? Everyone?
Capacitor.
Yep. Combination of a capacitor and an inductor makes a tuned circuit. Okay, the function of a single pole double throw switch. Single pole means that it's one circuit. Double throw means it can go between one way and another way. So a single circuit switched between one of 2 other circuits. Single pole, double throw. A relay is basically a coil of wire that pulls in an electromagnet. It fires an electromagnet which pulls in a contact. So it's an electrically controlled switch. That's a relay. A meter is a device that displays an electrical quantity as a numeric value. So if you have a voltmeter, what's that going to measure?
Volts,
If you have an ammeter, that's going to measure?
amps.
Yep, current. If you have an ohm meter,
Ohms.
Ohms.
it's going to measure resistance. That's right. A device that combines several semiconductors and other components into one package. They are integrated together. That's known as an integrated circuit. And what type of circuit controls the amount of voltage from a power supply? That is a voltage regulator. And what do we call something that converts AC into DC? That's called a
Diode.
Oh, it's a diode and it's a rectifier. It rectifies AC into DC. Electrical component used to protect other circuit components from current overloads is a fuse. Okay, so now We talked about this kind of. I'll bet you guys know why. Which of the following is a reason to use shielded wires? What happens if you have a wire carrying a current? What does it make?
Yeah,
What kind of field?
Magnetic.
Magnetic.
magnetic field,
And what does a magnetic field make? A magnet.
energy.
Now, a current makes a magnetic field, and a magnetic field will make a
current.
current. What if you have two wires that are in parallel?
It'll bleed over.
It'll bleed over. That's why we use shielding. The shielding prevents that from happening. Okay, radio wave characteristics. Hey, do you guys remember yesterday when we did that? That was yesterday.
With the ohms.
When we did
Yeah, we did the,
when we did radio waves. That was yesterday. But now we're going to go a little bit further into it. Okay, so we're now going to get into HF propagation. All right. Does everybody remember when we talked about radio waves yesterday?
That was when we were talking about the Earth and the atmospheres.
Yep. Remember the names of the layers?
E, E, and F.
D, E, F. Okay. And
Mhm.
F splits into F1 and F2.
Yep.
Okay. The highest frequency that you can use that reflects an energy back. Remember what that was called?
Muff.
That was called the muff. That's right. The lowest energy, the lowest frequency you can use that will pass through.
Luff.
That's called the luff. Yep. Okay. So if the luff is higher than the muff, then nothing works. That can actually happen. You know, if you get a good solar storm, that can actually happen and you get a radio blackout. Fortunately, that doesn't happen too much. Okay. Now, I'm going to open this up so I make sure I know what I'm talking about. Okay. This whole blob up here is known as what part of the atmosphere?
Ionosphere.
Ionosphere. And the reason it's the ionosphere is because
The sun's
Yeah.
making ions out of hydrogen and oxygen.
oxygen and nitrogen. Yep.
That's
So
what
you
I meant.
have all these electrons floating around up here that make a charged field, and you have ionized nitrogen and oxygen, and so you have electrically charged particles. Okay, so why do we use HF? The ionosphere refracts and bends radio waves, but why would we use HF versus VHF? And that's because we can,
more deflection.
yep, you get some really long distances. So long distance ionospheric propagation is very common on the high frequency bands. During peak of the sunspot cycle. Okay, so the sunspots are a function of solar activity, and they are basically correlated to the amount of ionizing radiation coming out of the sun. So the more sunspots there are, the more solar activity there is, the more ionizing radiation, the greater the level of ionization up here in the upper atmosphere. The more there is, the higher the frequency you can use. So what we're going to do now is we're going to look at our band plan. And has anybody spent any time looking at the band plan?
Yep.
Yeah, okay. So this is the band plan. This is basically a large part of the map that we are allowed to use. So if you were to look at the overall band plan, notice that the frequencies are not actually contiguous. There are many different things in between the ham bands. So the higher the frequency you go, notice we're down at 4, 7, 10, 13, or 14, 6, 18, 21, 24, 29, 50, 148. In order to use higher frequencies, you need higher and higher and higher levels of ionization in the atmosphere. So if we were to look at the 10-meter band during the time when the sun is not particularly active, the 10-meter band is basically dead as a rock. You could listen for a year and hear nothing. However, when the sun is really active, which is at the top of the sunspot cycle, we would hear typically a lot of things. And it gets very interesting for a couple of years until the sun's activity starts to go down. So at the top of the sunspot cycle, we might even hear, and like when we were looking at the beginning of class, we were looking at a map and we noticed that the East Coast was actually hearing on 6 meters, which is VHF. They were actually hearing into Europe, and some of them were hearing into the Middle East. That is probably F layer propagation just because of the distance. And it is possible at the highest part of the sunspot cycle during the day when you get maximum ionization that you could actually work 6 meter F layer skip. So it's not that common. It's really exciting when it happens and then it disappears. So there's a kind of a saying, which is when the 6 meter band is open, you better go and use it because 15 minutes later, it probably won't be anymore. Okay, during the day, the higher bands, because of higher levels of ionization, the higher frequency bands, shorter wavelengths will work better than the longer wavelengths. So, all right, I'm going to go back over here. Right there. Okay. What is the best time for long distance 10-meter band propagation? And that's from dawn to shortly after sunset, whenever there's a lot of sunspots. So we are actually coming up to the top of the sunspot cycle. Everybody's very excited. And again, the 10-meter band, which even a technician has access to using voice, can be very, very interesting. You can talk all over the world using it. A likely cause of irregular fading of signals propagated by the ionosphere. Remember yesterday we briefly talked about multipath. Did we talk about multipath yesterday? I think so.
We did.
Where a signal might take a little bit longer to get from point to point. Well, if we're bouncing things off of rocks typically aren't going to move a whole lot. But uh-oh, somebody's got feedback. Okay, I think I got it. Okay, so rocks are typically not going to move a whole lot. Buildings are not going to move a whole lot, but the ionosphere is 500 miles up and those clouds are continually shifting and moving. And what happens is if they go up by 20 feet, all of a sudden the path that you had a second ago isn't really good anymore because you might have signals that are taking 3 different routes to get to you and they cancel each other. If you wait another 15 seconds, they might come back. So that's irregular fading. And it basically, Max, did you experience any of that this weekend? Where a signal would be really strong and then
Yes.
then it would suddenly come back.
Yep.
It's kind of an amazing thing.
Yeah.
Okay, now we have not talked about polarization yet. We're about to talk about polarization. So the direction of the electric field is the polarization of the wave. That is the definition of the polarization of the wave. So if everybody holds up their right hand, which finger is the electric field? You remember?
The pointer.
Nope. Your thumb
Middle
is the electric
finger.
field. Your thumb is the electric field.
Mhm.
Index finger is a magnetic field. And the point and your middle finger is the direction of movement of the whole wave. So could you have a wave that is always going the same direction, but the electric field and magnetic field are continually rotating? What do you think? Could you do that?
Circular polarization.
That's actually called circular polarization, where they're always changing. Now, you could also have it where your thumb is parallel to the ground all the time, right? That wave would be horizontally polarized because your thumb is parallel to the ground. You could also turn it so that it was always up and down. That would be a vertically polarized wave. Once a signal gets up into the sky, if you're talking about high frequency, by the time it gets absorbed and re-radiated and twisted around, it's known as elliptical polarization. There's some vertical and some horizontal and some everything in between by the time it gets back to you. Because of that, when you're building an HF antenna, it really doesn't matter what the polarization is. For VHF, it is actually extremely important because let's say that you are expecting a signal electric field to be going down, up, down, up, down, up, down, up, and instead it's going horizontally, back and forth. How much movement of electrons will this actually make in your antenna that's looking for that? What do you think? If it's expecting signals to be going back and forth, if it's expecting movement back and forth, and it's straight up and down, how much ability is there to move things back and forth in this?
Not
Not
very
a lot.
Nothing, virtually nothing. So if it's polarized, if it's cross polarized with respect to each other, they basically will almost pass through each other as if they don't even see each other. That's why if you're trying to receive somebody that's using a vertically polarized antenna, you need to use a vertically polarized antenna, at least on VHF and UHF. If someone's using a horizontally polarized antenna, you need a matching polarization to hear them.
So when you're using an HF, then you need to hold that antenna straight up and down.
No,
not side.
VHF. HF, it doesn't really matter.
That's what I meant is
Yeah.
2 meters. Yeah.
Yes. And there's a reason for that. And that's because if we look at, we're actually getting into antennas and feed lines right now.
Yeah, I meant an HT, not an HF. I'm
Oh,
sorry.
yeah. Okay, we're doing antennas right now. So antennas and feed lines. Okay. Antennas and feed lines. A simple dipole antenna oriented parallel to Earth's surface that is going to have an electric field that is back and forth, left and right, which is going to be parallel to the Earth, which is horizontal. A half wave dipole, we're going to draw one of those in a second, has a signal that emanates broadside to the antenna. And you know what? It's time that we actually start drawing stuff because a picture's worth 1,000 words. Okay, so here's the Earth. I don't know why I put it on a slope. I guess I was thinking about Max's house. Yeah. Okay. So here is an antenna. Notice I drew a left half and a right half. It doesn't actually have to be a left half and a right half. I just made it convenient. Here's my feed line. And here's my antenna. I have selected my antenna for a given frequency so that it is 1/2 wavelength long. That is my total length. This is the simplest and easiest antenna to build. This is a half wave dipole. Dipole because it's 2 separate pieces. The feed line, what is the purpose of this feed line?
To
Signal
transmit
from-
the power into the dipole.
Yep. That the purpose of the feed line is to connect the transceiver or transmitter to the antenna. That is the purpose of the feed line, to be able to move power, electrical energy from here at the bottom up through the feed line into the antenna where it can be radiated into space. Okay, now, if I were to look at this, this is moving back and forth. If we were to figure out exactly how this works, now this is going to make more sense. What is the current at the end of a piece of wire? I asked this question yesterday.
0.
0.
It's 0. That's right. Now, if I draw a wave that is a full wavelength long, how much of that wave will be able to exist on an antenna that is a half wave long?
Half of it.
Half of it. Okay. By definition, where is a 0 on this on this graph down at the bottom.
In the center.
There's a 0
At the
right there,
180.
and there's a 0 right there. So therefore, my current on my wire must look like this. It has zeros at the ends, and sometimes it's going to look like this. And sometimes when it's transitioning, it's going to look like this. It's going to be getting bigger and smaller, but it's always going to have zeros at the ends. Well, that means that if my maximum current translates to my minimum voltage, which it turns out it does, by Ohm's law, E is equal to I times R. Everyone agree with that?
Mhm.
Well, because we're dealing with complex impedances, we're dealing with impedance, which is actually Z. We're going to use Z there. We're going to solve, we're going to make EIZ. We're going to solve for Z. Z is equal to E divided by I. Now, this is kind of an empirical thing. We're not going to use numbers here. But if I am feeding this at the current maximum, which is right in the middle, and current max translates to voltage minimum, then my voltage is going to be, we're just going to say it's low. And what is my current at the maximum? It's low divided by high. What is something that is low divided by something that is high?
Equal.
Negative.
Well, it's going to be low. Right? Something small divided by something big is going to be something small. But now let us take this and try to put power into the antenna way over here at the end. Z is equal to E divided by I. What is my current right here? How high does that go?
1/2.
No. What's the current at the end?
Zeros.
And I'm feeding it really close to the end. So it's not going to be a high current anymore, is it?
No.
So my voltage actually at that point is going to be high, and my current is going to be
Low.
Oh,
So what is high divided by low?
high.
Low.
High. So depending on where I put my feed line, that is going to change what my impedance is. Has anyone ever heard of an end-fed half-wave antenna?
Heard the phrase.
This
Nope.
is an end-fed half-wave antenna, because where am I feeding it?
At the end.
At the end. It's an end-fed half-wave. So my feed point impedance for my center fed dipole is about 70 ohms. My feed point impedance for my end fed half wave is about 2200 ohms. Okay, so the next part of this is my
Okay, pause.
transmitter. Go ahead.
So we just know 70 and 220.
Or 22. You don't have to actually know these. You just have to know high versus low.
High and low. Got it.
So, but now there's a couple of things to do here. Transmitters by default, by definition, because of the way electronics were designed and power transfer, and it's actually a pretty deep subject, are designed for 50 ohms. This you do have to know. That is the feed point impedance. That is the characteristic impedance of many coaxial cables, and that is the design impedance of most transceivers on the market and that have been made in the last, 75 years. 50 ohms is the impedance that they look for in the real world. Well, okay, 70, would you agree? Not so bad, right? 70 is not that far from 50. How about 2200?
It's high.
Yeah, it's
Not
really
so
high.
bad. That's really bad.
High. So, well, we have a fix for that. So there's a couple of things you can do. One, you can make a box and put it down here at the bottom, which has this in it. Anybody recognize this?
It's an antenna tuner.
That's an antenna tuner. Yeah, you can do that. You can do that. But the other thing we can do up here is, you remember we up at the upper left, we drew something like this a little while ago.
Transformer.
That's a transformer. Well, it can transform voltages, right? Remember that other little thing that I showed you about the resistances and stuff? If I have, let's say a transformer that has a 7-to-1 turns ratio in it, that has an impedance transformation available of the square of the turn ratio, which is 49-to-1. So if I have 2200 ohms over here, for instance, I will get, let's see, about 44 ohms over here. Because it transforms impedances as the square of the ratio. Well, how about 44 ohms? What do you think compared to 50?
A lot better.
I can deal with that. And that's why when you build or buy an N-Fed half-wave antenna, you need to have an impedance matching network. And it's usually in a little box up at the antenna. It's designed to transform the impedance from one to another that you can actually work with. Okay, so now what we're going to do is we're going to take our antenna and we're going to figure out how long to make the thing. Here we go. This is the real meat of everything. So we're going to pick an antenna that is going to be cut for, let's say, 21.0 megahertz.
God, I have one quick question about the previous.
Yeah.
Is there a reason why we should or should not use a center fed as opposed to an N-fed dipole?
People like N-Feds because the impedance is so high, pretty much independent of the frequency that you pick, that you actually don't even really care if they're resonant or not at that point. You're going to be presented something that's a high impedance no matter what. And if you can stuff power into it, it'll radiate somehow. So it's a multi-band antenna. Now, the problem with a dipole is a center fed dipole is that the impedance might be 50 ohms. It might be 10 ohms. It might be 800 ohms. So you need a lot more ability to tune it. You need an antenna tuner that has a much wider range to make it work. That's why people like N-Feds.
Is there any reason to use a center fed then?
Depends what you're feeding it with. I use ladder line, and I use a transformer on my ladder line, and I transform that to something which I then tune. And ladder line has almost no loss, whereas coaxial cable does. So that's a design consideration. There's also where are you going to hang it? How are you going to put it up? An N-Fed, you just need to support one end pretty rigid, with something rigid, and the other end it's just like hanging in a tree. So you only need two supports, whereas a dipole, you're going to have the cable hanging up in the air, and either it'll be hanging from the antenna, which puts a load on the antenna element, and then you have to support both ends. So that's why people like the N-Feds.
So there's no real disadvantage to using an N-fed then?
Not really. I mean, once you get power into the antenna, a piece of wire is a piece of wire. If it has current, if you can get voltage and current into it, it will radiate.
When N-fed's a lot easier to deal with, why would anybody ever use a center fed?
Because you still have to build a transformer for it. You have to have a support, some way to support that transformer up in the air.
Okay, go ahead.
That and the fact that some people, there's really, honestly, there's no real disadvantage of using an N-Fed other than the fact that, again, you have to have a transformer box.
Well, I have to use a balun on my center fed anyway.
Depends how you build it. Like I don't have a balun on mine because it's ladder line.
Yeah, but is your antenna tuned for a specific frequency?
It is not.
It is not.
It is not.
Okay.
So
All right. Yeah.
I got a question. I have the auto tuner and a 213 cable up to the copper wire antenna, about 27 feet long. I hooked up the center wire, the core of the 213 onto that end fed piece of 27. Where do I hook up the shield?
Uh,
I have it loose at the moment.
that's a good question. It's really, it doesn't so much matter.
It doesn't matter.
Really doesn't.
Because
mean,
it's
there's-
not hooked up on the tuner, it's not hooked
No.
up on the wire.
No. It really doesn't.
Okay.
I mean, effectively, there's a short counterpoise wire, as far as I can tell.
Okay.
You know, so that you don't feed it directly at the end, but essentially it's almost at the end.
Okay. Thanks.
Okay, here we go. We're going to calculate antenna lengths. So we have to figure out what the wavelength is in free space for 21.0 megahertz. So who's got their calculator handy? It's good practice to use that calculator. How do we write this formula? 300 F and lambda. Okay. What's the thing that we don't know, everybody?
Lambda.
Wavelength, lambda. Okay, so we cross that out. 300 divided by 21. And what do we get?
What
What was it? 14
2 9.
Okay, 14.29 meters. That is the wavelength in free space of a wave of a frequency 21 megahertz. Okay, good. Now, what size antenna are we making? We're making a half wave antenna. So take half of that.
Where did that 300 come from?
Speed of light.
Right.
That comes from the speed of light.
7.14.
7.14 meters long. Okay. Now, what we're going to do is we're going to take 95% of that, because wires are not infinitely narrow. They have a little capacitance. They have a little bit of inductance, self-inductance. So what happens when we take 95% of that? What do we get?
6.78.
6.78 meters. Okay. So that is ideally the total length of our antenna. So now if we wanted to actually, you know, let's say you don't have a metric tape measure, you're going to multiply that by 3.3 feet per meter. What do we get?
22.4.
Okay. So that's about 22 foot 5 inches. Okay, there we go. So you want to make a perfect half wave dipole, cut it in half. What do you get for each leg? About 11 foot 2. There you go. That's a resonant half wave dipole for 21 megahertz. That's how you build it. That's how you make an antenna.
And that works on one frequency.
That works. Well, it is resonant on one frequency. That is a really good question. Let us say that, well, okay, there are two boundary conditions that always have to be met. What are those two boundary conditions?
Impedance.
Nope. Look at the wire, and there are two boundary conditions that always have to be met by physics.
The endpoint in the
The
center,
endpoint has to have what current?
zero.
0. Okay, good. So I have 0 current at the endpoint. So let's say that we have this antenna, and now we know that we made it so that at the design frequency, it looked like this, right? It was perfect. But now what we're going to do is we're going to have 11 foot 2 and 11 foot 2 and 22 foot 5 for the whole thing. right? Which we know to be true. Now we're going to see what the darn thing looks like at, let's say, 10 meters. So we're going to pick 28 megahertz. Okay, somebody go through the frequency and wavelength calculation again for me. Lambda is equal to 300 divided by 28. What do we get?
1.0714.
I hope it's 10.
It's 10.71.
Okay, 10.71 meters. Multiply that by 3.3, please.
35 feet.
35.35.
Okay, 35.35 feet. Okay, so that is one full wavelength. And multiply that by 0.95 to account for the real world. What do we get?
33.58.
33.6
We'll go
about.
with 33.6 feet. Okay. So along that antenna, we get a full wave that is 33.6 feet. And so what is a half wavelength of that?
16.8.
Okay, so that's a half wave.
Do we lose anything for the connections in the middle?
Nope.
Does that add or detract?
Nope. You can pretty much ignore that.
Okay.
And okay, so that's a half wave is 16.8 feet. So, well, what do we have up here for this antenna? How long is it?
We're at 22 for the
22
existing
feet, 5
antenna.
inches. Okay, what is if we draw our half wave, it has to be how long for the 10 meters? 16 feet, let's say 10 inches. Okay, which means that the center point would be at about 8 foot 5 inches. Okay, that's the highest point. Well, we can start at the end and we start drawing our waves on it. And well, where does 11 foot 2 put us? Somewhere about here. So our pattern looks like this, our current looks like this. And we do the same thing on the other end and our current looks like that. So we're not feeding it at the current maximum, but that's not bad. You know, that's actually a pretty decent antenna. It'll work. But now we're going to pick a different one. So we're going to pick a different frequency. And we're going to pick the 40 meter band. We're going to go 7.2 megahertz. So somebody tell me what the wavelength is. 300 divided by 7.2.
41.66.
Okay. Multiply by 3.3.
137.5.
Okay. So that's 137 feet. Take 90% of that or 95%.
130 feet plus 0.62.
We'll go with 131 feet. Okay. So that's a full wave, which means a half wave is 65 foot 6 inches, which is about what it is. That's a half wave. Okay. So we're going to draw that. This is 65 feet 6 inches, and a half of that is about 32 feet 8. Okay. Do you guys see a problem here?
Well, if
You
you
see a
got
problem?
22 feet of wire in the air, and
That's
you're
right.
trying to cover 65 feet
So
of
your
wire.
current is going to look like this. It's still going to be going up. It's never going to get anywhere near the top. And it's from the other end, it's going to be going up and it's never going to be near the top. So you're feeding it at the maximum, but ideally your current maximum is about this high. So how much can you actually feed into it? That antenna is never, because current is what makes energy fly off into space. Since you can't get current to flow in it, how efficient is it going to be?
50%.
Oh, well, probably a lot less than that.
So is efficiency the same as resonance?
No, efficiency is, well, okay, maybe not efficiency in this case, but effectiveness. How effective of an antenna is this going to be?
Not very good.
Not very good. This is a really poor antenna for that band. And that's why you can typically use an antenna for its design frequency above that frequency. But if you go lower, it really, goes downhill fast.
So if it was a full wave being, the 130 odd feet, then overall, then it'll be a more efficient antenna, but we don't always have, 130 some odd feet to work with in our backyards.
So I actually have 132 feet of wire in my yard going in one direction. And I have going in the other direction, I have 66 feet. So this 132 feet is a half wave on 80 meters. And the 66 footer is a half wave on 40 meters. So the one that's 80 meters, I can use this anywhere up to 6 meters. The one that's on 40, I can use this anywhere up to 6 meters. But I cannot use that antenna on 80. I can't use this other one on 160. It just does not work. I can't use this one on 160.
So you just pick the bands you want to work and calculate your antennas accordingly?
Yep.
So how do we pick a band?
Well, you go back to this. If I can find it.
I ran into that problem.
You go back to this.
But what do you want to do? I don't know.
Yeah, well,
Which one? Which
you gotta
band is which? They all looked alike to me.
they are not alike. They all behave differently. Where do you want to
The
work?
most popular bands are like 40 meters and, and 20 meters.
20 is the worldwide. 20 is kind of like the worldwide superhighway.
Okay.
And this is where, knowing how the frequencies are going to behave really becomes useful. And if you want some more information on that, then you start looking at things like this. Hopefully this opens up. And I go to all bands. And hopefully this opens up. And this is where understanding how different frequencies behave becomes really helpful.
So when you were taking the half of the wavelength, that's for the height of how high up the antenna has to go, right?
Nope. That's for how long it is. Okay, so here right now, for instance,
No.
Go ahead.
When you you had like the half wavelengths on each side, but for how you kept like drawing the dot above that. What was when it goes like higher up?
Oh, that's how that is the peak current that should be available. But I never got to that point because the antenna wasn't long enough. I couldn't draw waves on there. I'll show you. I'll go back and show you in a second.
Okay.
So,
Yeah, I
okay.
didn't understand the peak current thing.
Yeah. Okay. So this is 20 meters right now. Come on.
We're still on
You're
the
not
diagram.
showing that screen.
Oh, sorry. Sorry, different browser. There we go. Thank you for pointing that out.
Yep.
Okay. So this is from Oregon, what 20 meters looks like right now.
Wow.
Yep. Now, if I were to say, okay, what does 80 meters look like right now? I'm going to guess that there's absolutely nothing. What does 40 look like right now? Probably almost nothing. Yeah, nothing. What does 30 look like right now? Probably almost nothing because nobody's on it. How about 17?
Nobody's on it.
Oh, yeah,
by
there's
personal
17.
choice or by conditions.
Both. Because if the conditions are, if the band is useless, why would you be there? Why would you waste your time on it? It's daytime. 40 meters is basically dead because of the D layer. So that's where knowing this stuff and having some understanding of how propagation works becomes really useful. So 12 meters it looks dead. 10 meters, we'll see if there's anybody. Nope, there's one person on 10.
But he's talking all the way to Brazil.
Yep, and that's trans-equatorial propagation. When the conditions are really, really, really good, what you'll have is 10 meters open from the west coast to Europe, for instance. And that goes over the polar route, which is a much more difficult route. Because if you think about it, the sun is directly overhead over the equator. So your maximum ionization occurs right over the belt of the Earth. So, okay, so let's go back to drawing currents, right? Ideally, you're going to have on a dipole, you're going to have this, a nice smooth curve with the maximum at the center, right?
Distance here.
Chance, right?
Yeah, gotcha.
Okay, so you're going to have the maximum right at the center, and it's going to be the peak. This is a nice clean wave. But let's say that the wave that you're actually working with is actually this long. By definition, this has to be there. And this other point at the other end has to be right there. So if you start drawing this wave, this point right here is going to be there. And this point here is going to be there, which means that all this stuff, the really high current spot in the middle, you're never going to get to draw it. There's no room for it. You can't. I mean, basically you get to this point and you never, you basically have to take this section of in the center and saw it out. And then it drops off like that. So you never made it to the point where this happened because it would be off the end. And by physics, you can't do that. It doesn't work. Understand?
You can't just saw that piece out of the middle and throw it away.
Well, essentially that's what you're doing. It doesn't exist when you try to put that wave on the smaller antenna.
How are you calculating the peak current though?
Oh, well, I mean, the peak current is just from the picture of the wave.
Oh, okay. All right.
I mean, the wave looks like this. It's a half wave. It's a piece of a sine wave. But I can't do this part in the middle. There's no place to put it because this part exists like that. This area goes into here. This area on the left goes into here. There's no room for all this stuff in the middle. And the middle part is the big meaty part that is going to radiate the most energy.
So you take that out by a tuner of some kind?
No, you take that out by building a longer antenna.
So you end
This-
up with 14 antennas in your backyard?
No, you end up with the longest antenna that you can possibly put up.
And then work short from there.
And just work short and work higher frequencies with it. You put up the biggest piece of wire that you can.
Quick question for you.
Uh-huh.
So when you were looking at those charts that were showing 20 meters bouncing all over the world and whatnot,
Yep.
I noticed that there's not a lot of short range. Does it still cover the ranges inside of that? So in
Nope.
other words, if you wanted to talk to
Nope.
Portland,
Nope.
no.
And you're going to tell me why.
Well, I know that I've heard of the shadow effect.
It's the
Well,
skip zone.
It's the skip zone. And this comes down to geometry.
You can't get up to the sun and back, or the, whatever that layer of the atmosphere is, and back down in the short distance from your place to Portland.
Yeah, your angle of incidence on the ionosphere is too steep for it to be refracted back down. So it just goes on through.
What if you build an invis antenna? Have it
Well,
put
that
off the
would
ground?
help. That would help.
Just a regular cloud burner.
You still have the issue of how are you going to get the ionosphere to do what you want it to?
That depends on everyday conditions.
That depends. That's right. So if I were to look at that, okay, well, it turns out that certain bands, so here's the F layer of the ionosphere. the angle of incidence of the signal going up, there's a critical angle at which it bounces back down. Depending on the band you're on, it might be like 80 meters at night. A signal that goes up like this can actually be refracted back down. And this would be something called NVIS, which is near vertical incidence skywave. But that's not going to work. This is like on 80 meters at night. And this would be like 20 meters. NVIS typically does not work on NVIS. And 20 meters doesn't usually work with NVIS. The only chance that you have is that not all the energy goes forward. Some of it gets scattered back. And this is known as backscatter, but it's not very reliable. But it allows people, it sometimes allows communications within the skip zone. But usually
Scott,
this is way weaker.
How do you change the angle of the radio wave? Now the NVIS is going almost straight up. The 20 meters is going off at about 45. How would
Well,
you change that angle?
So if you have your antenna typically is going to be hopefully a half wave above the ground.
Uh-huh.
That will, okay, so a dipole radiates largely perpendicular to its axis. Right? If I were to have a dipole that was in this orientation, it would radiate that way, but also up and straight down. It basically forms a figure 8 or think of it as a donut around the antenna wire. That's what a dipole radiates like. So if I were to draw like a donut that looked like this, and it goes a vertical donut. If I were to turn it on, make it so the dipole was up and down, my donut would look like this. It'd be a horizontal donut. So I'd have radiation that way and that way and that way and that way. So think of a figure 8 or a donut. Now, what happens is ideally, if you are trying to work somebody far away, you don't want that angle, you don't want that radiation that goes straight up and down because it just usually goes through the ionosphere. So if you get your antenna a half wave above the ground, that will get a nice amount of horizontal radiation. If you want your signals to go largely up and down, straight up, and you're on 80 meters. Sorry, I drew your property again, Max. So if you take your antenna and you put it like 1/10 of a wave above the ground, you will have a great amount of energy going straight up. This is also known as a cloud warmer. Right? That's a cloud warmer. Normally, for people who are trying to work long distance, this is not a good thing. However, if you're trying to do NVIS on 80 meters, which is within 200 meters, 200 miles at night, this is a very good thing. So that's your use of, go away. So that's your use of NVIS.
So by raising my dipole up and down in relationship to the ground, I can change the angle of radiation.
Yep. That's why antennas are so cool, because there's many, many things you can do with them.
And if I send $300 to England, I can buy an antenna that works all frequencies. It sounds like some kind of a magic piece of machinery.
For $25, you can build it yourself.
Oh dear.
Yeah, see, that's the other reason that antennas are so cool. It's about ingenuity and figuring out what's going to work on your property. And you don't have to spend a lot of money on it.
So if I go back to this longest wire that I can fit on my place, then I can tune down from the longest wire and make it pretend it's short.
When you say tune down,
An antenna tuner.
well, I mean, you can use it on shorter wavelengths.
You know, there's a website.
I can use a longer wire on shorter wavelengths.
Yep. You can use a longer wire on higher frequencies. The closer you get, basically the higher the frequency you get, the more omnidirectional the antenna will get. That's one disadvantage of doing that. But at some point, your signal's getting out, so you just don't care. If you want it to be optimized, then you have a different antenna for every band. I don't know many people who do that because it gets really expensive.
You can go to sodabeams.com and it's a site over in England, and you can get, antenna kits from them.
Mm-hmm. Yeah, you can buy lots of single band antennas.
Well, you can get, multiband. You can get
You
link
can get multi-band
dipoles as
too,
well,
yeah.
or NFEDs, and
Well, you can get parallel wire dipoles
right.
as well. Three dipoles hanging off of one piece of cable.
Yeah, those of us that are doing SOTA, I mean, we're just using, 10 to 20 watts of power, and we're getting out all over. So you ought to be able to do it on 100.
Okay, so now that we've talked about that, we're going to go back to the book. And okay, a simple dipole oriented parallel to Earth's surface is horizontally polarized. The polarization is the direction of the wire. In which direction does a half-wave dipole radiate? That would be broadside. So if your antenna is looking like this, it would go up and out and back and down. Virtually nothing is translated in the direction of the wire itself. Okay, the approximate length in inches of a half wavelength 6-meter dipole. Somebody is going to walk me through how to do this. Come on, who's going to volunteer to do it? Somebody walk me through it.
300 divided by 6.
Okay, so my frequency is 50 megahertz roughly, because my wavelength is 6 meters. And now that was a bit of a jump, but if you know the chart, you know that our frequency is 50 megahertz. So that's actually good. Okay, so 300 divided by 6 is 50 megahertz. And so we're actually going to build it for 50 megahertz. So how long does our antenna have to be?
Is it like 20? I don't know.
Well, what's our full wavelength?
300 divided by 50.
Divided by 50 is
6.
Okay, that's our wavelength. Okay, now they said specifically a half wave antenna. What's a half wave?
3 meters.
3 meters. Okay. And that's going to be too long. What do you have to shorten it?
0.95.
You have to multiply by 0.95 is 2.85 meters. And then what do we get? We have to convert that to inches. We can convert it to feet and then to inches.
0.33 feet per meter. 3.3.
3.3 is equal to about 9.3 feet. Okay, times 12 inches per foot. What do we get?
112.
112 inches. Okay, so we got 112 inches. Now, if I put this on an antenna analyzer, which basically can sweep from, let's say, I don't know, 48 to 58 megahertz and go outside of the ham band, and I find that my standing wave ratio of my antenna 1:1 is perfect, and infinity is way up top, and it goes like this. And I find that this occurs at 51 megahertz, but I really wanted it to be resonant at 52 megahertz. What would I have to do with my antenna?
Make it a half-inch longer.
Think about that. If I wanted it to be a higher frequency, what do I do with it?
Have to be shorter.
I'd have to shorten it by a little bit at a time. What if I wanted it to be down here at 50?
Add some wire to it.
I'd add some wire to it. So there is a good rule of thumb. It's a lot easier to make a wire shorter than it is to make it longer. Because otherwise you got to solder and do all other kinds of stuff. So when you cut an antenna wire, what do they say? Measure twice, cut once. But then on top of that, you want to make sure that you're always starting too long, because you can always trim a 1/4 inch at a time. Okay. Which of the following increases the resonant frequency of a dipole?
Shortening.
Shorten it. Okay, very good. So the approximate length in inches of a quarter wave vertical antenna for 146 megahertz? Well, let's go through it. Somebody take me through it. What's the first thing I do? 300.
Divided by 146.
Yep, 300 F lambda. Okay, I don't know the wavelength. That's 146. What's 300 divided by 146?
2.05.
2.05 meters. And they said, how long is the antenna? It is a quarter wave. What do I get? 0.51 something meters.
Yep.
Okay. And then what do I have to make the antenna length? I have to shorten it
by 5%.
By 5%. So 0.95. What do I get in meters?
0.48. So I got.
Okay. Times 3.3. What do I get?
1.6 feet.
Okay. Times 12.
That's 1.6 is
1.6 times 12 inches per foot. Get about 19 inches.
Yep,
There you
19.3.
There you go. Quarter wave antenna for 2 meters, 19 inches tall. And then you have radials, which are the other half of the antenna. This is a quarter wave ground plane vertical. So that can be your ground plane. You can also have an antenna that looks like this, which is sitting on the roof of your car or on a truck or whatever. That's 19 inches tall. So where is the other half of the antenna?
You just said it was in the radials.
Yeah,
Or the
yeah, but how about on a
truck.
truck?
In the
It's in
coils.
the truck.
It's the body of the truck. Yep. Okay. Now, here's another one. Let's say that we have this antenna. Has anyone ever seen a mag mount? Anyone ever seen a mag mount antenna?
Mhm.
Magnetic mount? A mag mount looks like this. 19 inches. This is what I use on my car. So here's the center conductor that goes to here. And here is the shield.
The rubber
Okay.
thing at the bottom is a shield.
Yep, that's where my shield wire goes on my
Oh.
cable. Okay, so that being said, how does that work? Considering that the other half of the antenna is essentially, the easiest way to describe that is if I were to draw somebody far away. So here's me looking with my eye at an antenna that's a quarter wave above the ground. What do I see? I see a quarter wave antenna, right? What if this antenna were over a perfectly reflective surface and I didn't know it was there? What would I also see when I was looking there?
The other half reflected.
The other half reflected. I would see, if this is a quarter wave high and this is an
38
imaginary quarter wave, what does that make?
Half wave.
That makes a half wave dipole and it's vertical. But since it's not physically there, it requires a conductive ground plane below it. So this is a quarter wave vertical. A quarter wave vertical needs to be over a conductive ground plane in order to work properly. The ground plane effectively makes it look like there's another half of the antenna there. So if I have a piece of coaxial cable that looks like this, and this is the roof of my car, and this is a magnetic mount, the shield of my cable goes to a plate. How does it transfer energy to the roof of the car to make it look like the roof of the car is perfectly conductive?
With inductance?
Look at it again. I'm going to draw it. What is that?
The plate is the magnet.
A capacitor.
That is a capacitor. And since we are dealing with what kind of current, AC or DC?
DC.
DC.
No.
Oh, DC.
Radio frequency energy has a frequency, right? 146 megahertz. This is AC. Since we're dealing with AC, what does that capacitor look like?
Open.
Nope,
Is that short circuit?
that's a short circuit. So basically, it capacitively couples the mag mount antenna to the roof of the car. Electrically, it looks like the capacitor is, the antenna, the bottom part of the antenna is part of the car.
How can you have AC in a car? A car is DC, isn't it?
What's this? The car is DC, that's the power,
Yeah.
but what's a radio? What's radio wave? Does it have a frequency?
Oh, okay.
They're totally separate.
Yeah.
So basically, yes, you are basically resonating the body of your car at 146 megahertz.
Okay.
So let's ask this next question. Let's say that I have a handheld radio with a quarter wave antenna on it. And here's my hand. Okay. Here's my hand, and it's connected to my body and my head. I'm a terrible artist. And now everyone's going to know that I'm a terrible artist. Okay, there's me holding, God, that's an ugly drawing. There's me holding the radio. Okay, where is the other half of the antenna?
Your body.
The ground.
I am the other half of the
Yeah.
antenna. That's right. So when you're holding that radio, you are capacitively coupled to the body of the radio and are the other half of the antenna.
So you're resonating too?
Yep. You have current flowing through you. And if
Mhm.
you've been unlucky enough to touch a metal object, like a screw on the back of a radio case with a sweaty hand, you can get a nice little RF burn that way. Done that.
On this same note, if you're doing something like wearing a plate carrier and you've got your radio attached to it, is it still acting the same way because you've got the slight distance and still using your body?
If you're using a what?
A plate carrier, shoulder straps, backpack, something like that. You've got the radio attached to something other than
Oh.
held in your hand using a push button.
Yeah, probably so. I mean, depending on how far away it is, but yeah, I mean, it's still capacitively coupling to you.
Okay.
Have you ever heard of making a tiger tail?
Yes.
That's another way to do it.
A tiger tail connects to the shield of the cable and hangs down, and it's 19 inches long. So it basically makes a dipole.
So would that prevent current from going through your body then?
Well, which way is current going to flow? Through the what?
Path of least resistance.
And I would say a piece of wire is probably better than you are. So I would say more of it's going to flow through the wire than through you. I mean, it's probably not going to hurt you much, but still, just to keep in mind that, you're the other half of the antenna. Okay, here we go with antenna loading. And what I'm going to do is I'm going to draw an antenna and we're going to annotate. Okay, so this is a 19-inch antenna. This is also a 19-inch antenna. How come that's a 19-inch antenna?
It's
This
just
is also a
stretched out.
19-inch antenna.
Because the coils,
Is the inductors.
That's also a 19-inch antenna.
it's the same with curly hair.
Yep. So the total electrical length of that antenna, of all three of them, is 19 inches long. But what have I done with it? I mean, I could do this too.
You created an inductor.
I've created an inductor, which would change the impedance a little bit. So maybe you need a little bit of a capacitor to counteract it. But more importantly, I have taken my 19 inches of wire, and I still have 19 inches of wire. So it's still 19 inches of wire. So the transmitter is still pretty happy. But what have I done to the antenna? I mean, I could make an antenna that's this long.
Compacted it.
I've compacted it. There was an antenna for 2-meter band that was 2.5 inches tall. Now, what happens when you do that is if you look at how the energy is actually radiated, inside the coil itself, the currents that are generated make fields that largely cancel each other. And if we start drawing our currents, where is the current going to be zero?
At the end.
At the end. And so it's going to be maximum at the base. So if we draw our wave, quarter wave in this case, it looks like that. How about if we draw it on one of these other ones? It's zero at the end. And what's going to happen to all the high current? It's going to be compressed and it's going to be high down here. But all of this stuff in here largely cancels itself out. So what happens to the efficiency of the antenna? All the current that's being
Decreases?
made, yeah, all the current that's being made internally goes down. So whereas a full-size antenna, if that's our reference antenna, we could say that that has 0 dB gain compared to a reference. Some of these other ones might have a gain of minus 10 decibels, which means for every watt that we put into it, how much actually comes out as RF? What is 10 decibels translate to? How many times?
Triple.
So it'd be 1/10.
That would be 1/10. If we have 10 decibels of loss, if we put 1 watt in, we get 1/10 of a watt out. Now, there are certain times that might be okay. When might that be okay?
If you're standing next to the guy you're talking to.
Exactly. If you're standing right near somebody, or let's say you're at a repeater site, right? Let's say you're physically at the site where the repeater is. You could transmit 1,000th of a watt and still be fine. In which case you'd basically need almost no antenna at all. So it all becomes very specific to the application that you're using. If you're out in the country somewhere, or you're on a mountaintop 100 miles from a repeater, the full-size antenna is going to work a heck of a lot better than a coiled up antenna, also known as a rubber duck, or in some cases, we call it a dummy load. Okay, we're talking about beam antennas and gain and stuff like that. Okay. Okay, let's talk about a beam. The most common form of a beam is known as a Yagi. A Yagi has a driven element, which is basically a half-wave dipole. And these are space elements. The ones in front are known as the directors. This one is known as a reflector. And again, this is a Yagi antenna. The full name is actually Yagi Uda, named after the inventors. Yagi is what it's known as, though. So the driven element, again, is a half wave long. The reflector is slightly longer, and the directors are slightly shorter, which kind of gives it a forward-looking picture. This is going to have an antenna pattern that is focused toward the front with a little bit coming out the back. And because this is a dipole, there's virtually nothing coming off the ends of the wire. So when we start to look at this, if we were to just have a dipole antenna would look with a pattern like this, some forward and some backward, and it would be equal. The difference in gain between what the beam does and what the dipole does, this is known as the gain. How do we measure gain? What units?
Decibels.
Decibels. So this antenna might provide a gain of, let's say, 10 decibels, which means that if we put 1 watt into it, we would get the equivalent if it was going out in all directions of how much power? If it was 10 decibels gain?
1 times 10.
100.
Get 10 watts, the equivalent of 10 watts in the forward direction. So this would go down as well. The ratio of the stuff going out the front versus the stuff going out the back is known as front to back ratio, also measured in decibels. So we might have a front to back ratio of 20 dB. What is 20 decibels equal to? Well, that's 10 plus 10. And every time we have 10 decibels, what do we do to our power level?
Raise it 10 times.
10 times 10 is
100.
we will have 100 times more signal going out the front than the back. That's pretty darn good, right? The benefit of that is that if there's interference over here or 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 over here, we really don't hear it. It's a very efficient way to use the power that you're using. And also the pattern works for transmit and receive. It's a reciprocal, it's known as a reciprocal thing. It's reciprocal because it works for transmit and receive. The pattern that it makes is going to be identical for transmitting and receiving. So it'll receive and transmit better. Okay, now.
Does that mean that the TV antenna on my house 50 years ago was a Yagi and I didn't know it?
It was not, and we'll get to that.
Okay.
Okay, so compared to the peak, we could say that we want to know what kind of angle we get where we have half the power going out as in the center. This is known as a beam width. And okay, if we look at this, what's another way to say half power?
3 dB.
3 dB. This is known as our 3 dB beam width. The angle between here and here, where our power is half of what it is at the center. That's known as our 3 dB beam width, and that's an angle. So the more elements you put out front, they are parasitic elements. You don't have to connect them to anything. The more elements you put out front, the more forward gain you get. So why, if you have room to put up an antenna that looks like this, or an antenna that looks like this, if you have room to put it up, why would you pick the one on the bottom?
More gain.
More gain. You get more bang for your buck that way. Of course, this might be, 4 feet long, and this might be 14 feet long. If you don't have room to put it up, you do what you can. Okay, so now another form of this antenna, just actually somewhat different, looks like this. Tell me if this looks like your old school TV antenna, Vic. Does that look like your old school TV antenna?
Mm.
Okay. The way this works is that these are all separate elements and these are fed like this, where all of these are common. They alternate sides, and then the same thing on the other side. Does anyone know what this is called?
Logarithmic antenna.
This is called a log periodic. And each of these elements is related to the previous one, so that on any given frequency, typically 2 elements will be functioning as an antenna. The other ones kind of like are not part of the game. At a higher frequency, these antennas will come into play. At a much higher frequency, these elements will come into play. So really what it means is it's kind of like a self-selecting thing. But since there's only like 2 elements that are in play on any given frequency, what do you think about the gain?
Not a lot.
Yeah, so gain. But what do you gain? What do you get out of it?
More
bandwidth.
Yeah, you could possibly use this from like 50 up to 1000 megahertz and cover that entire range. This is really good for a TV antenna, because on TV you had 50 to 88, and you had 174 to roughly 300, and then again from like 480 up to 800 megahertz.
We still use our antenna.
There you go. This is why, because it covered all those different ranges of frequencies in one antenna. And that's a log periodic. You can build these for the ham bands too. The military uses these also for HF transmitting station because they can operate on a very wide range of frequencies.
Are these
Yep.
highly directional like a Yagi is?
They're not as directional. So yes, they are directional, but if you look at your front to back ratio, because you only have like 2 elements operating on any one, your front to back ratio is going to be lower.
Got it.
Well, weren't they really directional? Because I remember as a kid, I had
They
to
are.
turn the antenna for my mom.
Yes, they are, but they're not as directional. 'cause
Not
there's
as,
really only
okay.
2 elements.
Okay.
Okay, so let's say that we're comparing an antenna's gain. We are comparing it to something. So the reference antenna is a dipole. So that's known as a gain in dBd, decibels with respect to a dipole. Now, there's also, because what does a pattern of a dipole look like? What shape does its radiation pattern look like?
Donut.
A donut. Okay. Is a donut the same thing as a sphere? The answer is no. So a perfect radiator would have a radiation pattern that was in the shape of a sphere around a single dot. That does not exist, but that actually has a name.
It looks like an atom.
Yeah, well, it actually has a name. This is called an isotropic radiator. And the reason that I'm mentioning this is that compared to an isotropic radiator, which is imaginary, a dipole has 2.05 dB of gain. So it's actually 2 decibels better than that in this direction. This is known as dBi. And when you start looking at antenna gains, you will see that there are 2 different things. There are dBd and dBi. dBd will always be 2.05 dB less than dBi because they're measured against different things. They basically can be translated from one to the other, but it's really important when you're looking at an antenna to determine whether they're giving you a measurement in dBd, which is better than a dipole, or dBi, which is better than this imaginary thing which cannot exist in nature. Okay. What type of antenna offers the greatest gain of the choices? Let's go back to that. Okay, what type of antenna offers the greatest gain? 5/8 wave vertical, an isotropic. What is an isotropic radiator again?
Imaginary.
Imaginary, that's right. All directions with the exact same strength. Or a J-pole. There is such a thing as a J-pole, but a Yagi is nice in direction. What's the problem with the thing called a rubber duck antenna?
Low efficiency.
Low efficiency. Why would you not want to use a VHF transceiver with an antenna inside a car?
Race.
Because you're inside a metal car, right? It absorbs your energy. The advantage of a 5/8 wave whip instead of a quarter wave, it has more gain because it's longer. It actually has a lower angle of radiation. Now, it also, well, when you pull it into a garage, will tend to hit the door. It will hit the garage door. Okay, so now we're up to feed lines and connectors. Coaxial cable. Why do people use it? Because it's easy to use. You can bury it. You can do all kinds of cool stuff with it. And it tends to be, if you get it properly, it can be direct buried. It can get wet. It can be in the sunlight if it's UV stabilized and not disintegrate. So really easy to install, really easy to use. Impedance compared to resistance is the opposition to AC current flow. Unfortunately, it's also measured in ohms. We covered that this morning. The most common impedance of coaxial cable used in amateur radio is 50 ohms. Why is it 50 ohms?
Because that's what radios are designed to put out.
Because radios have a characteristic output impedance of 50 ohms. So if you hook it up to a 50 ohm cable, that matches the radio. Despite being most popular, coaxial cable has some disadvantages. Well, one of them excuse me, is we're going to pull up. We're going to talk about cable losses. And we're also going to talk about moisture contamination and ultraviolet and things like that. So connector types. Okay, so what I'm going to do now is stop sharing this, and I'm going to bring up my browser. This is one of those things that we talked about yesterday after we broke for the morning. So coaxial cable loss chart. We're going to look at times microwave. Oh, come on. That's not the one I want. Sorry.
The link up on the
There we
text.
go. Got it. Okay. Here we go. Coaxial cable loss chart. So can everybody see that okay? Okay. So notice these are different amateur radio bands. 3.5 megs is 80 meters, 40, 20, 10, 50 megahertz is 6 meters. And I want you to just pick one cable. Let's go with LMR 240 right here. Notice what our loss is per 100 feet for LMR 240. At 3.5 megahertz, it's 4/10 of a dB, which is very, very little. But now let's go up to 50 megahertz. What do we have? 1.7. And let's go up to 440 megahertz. Where are we?
5.23.
Yep. Okay. So now if we want to go through, we can estimate this and say, okay, 0.45 dB. How many dB is doubling or cut by half? How many dB is twice the power? It's one of those two numbers you got to remember.
3
dB. Okay, so 0.45 dB, that is basically nothing, right? Okay, so now let's go up to 144 megahertz with LMR 240. What's our loss for 100 feet?
2.95.
That's basically 3 dB. That means if we put 10 watts in, how much will we get out?
5.
You'll get 5 watts out. Where did the other 5 watts go?
Heat.
Yep, you turned it into heat. So now let's go up to 2400 megahertz. Somebody left an M out. How many decibels of loss are there up there?
Well, almost 13.
Almost 13. Well, that's a 10 and a 3. So what does the 10 do to you? How many times?
10 times.
3.
And the extra 3 gives you how many times?
2 times.
2.
2 times. And 10 times 2 is
20.
So 12.
20
20.
because you multiply, which means that you have 1/12 the power coming out that you put in 100 feet of cable, which means if I put 100 watts in, how much do I get out? 1/12 of it, about 8 watts, which means that you're burning up 92 watts in heat. So
What do you
if we,
mean by heat? Does that warm up the cable?
it does.
Okay.
Now, if you're trying to keep your cable from getting frozen, that's a good thing, right? But now let's take a look at a different cable. Let's look at LMR 400, just to the right of it. At 2400 megahertz, what's our loss?
6.6.
6.6. Okay, well, that's about a 3 and a 3. So the first 3 dB gives you how much?
2.
Yep, and the
2.
second 3 gives you
2.
So 2 times 2 is
4.
4. So that means we're cutting our power. We have about a fourth of it coming out, which means that of the 100 watts we put in, how much do we get out now?
25.
25 watts compared to 8 watts just by switching cable. And that's why we can do things like that. Now, the other thing is all these different cables are different sizes. Now, this is a very important distinction. So let's say we have a cable that has certain dimensions, right? let's take another cable and give it similar dimensions, proportionally speaking. This is a 50 ohm cable because there's a center conductor and there's a shield that has a space in between them. What are two conductors with a space in between them called?
Capacitor.
Capacitor. What is a wire called? A wire has inductance.
Inductance.
So it turns out we can model our cable and it looks kind of like this. And this goes on forever. And it has minimal loss. But now in reality, it's not minimal. There's some, and there's some resistive losses right here and here and here and here. But basically each of these is a kind of like a filter network. It also has an impedance. By changing the values of the capacitor and the inductor, which is done by changing the sizes of things, the spacing of things, the material that we use inside, that changes what the characteristic impedance is. That's our Z of our cable. If we put power in to a cable that's 50 ohms and we're running 50 ohms, and this has an impedance of 50 ohms, then the power should, if there are no losses, just come out the other side and never come back. If we have a mismatch somewhere, where we have suddenly a different impedance, it's kind of like tying a rope to a closet door and you whip the rope and you see, you hear the rope, you hear the door go, but you also have a wave coming back on the rope. You'll end up having some energy coming back. If it's perfectly matched, if the impedance is a perfect match, you'll never see any energy come back. So by looking at this cable, if we keep the same proportions, but we make it smaller, it's still 50 ohms. But now, what is the difference between big fat cable above and tiny thin cable down below?
Manageability.
Yeah, what else?
More insulation.
Yeah, it could be. But what do you see about the center conductor if everything has to be proportional? I could also make a 50 ohm cable that's this big.
Well, the distance between the two capacitive plates.
Yep. And how about the size of the conductors themselves?
Smaller.
And they have resistance, right? So bigger cable is going to have higher power capacity. And it's also going to have, therefore, lower loss. And so if you are trying to optimize your system and you have room to put up cable that at, let's say, a gigahertz, let's say you're running 1 gigahertz, you're running a TV station, you might use cable that has a diameter of 6 inches. This is really hard to manage, but if you have a 500-foot tower, maybe that's what you do to keep your power from getting lost. If you have a small antenna on the roof of your car, do you have any need to do that? The answer is no. You want to be able to slam it in the door. So maybe you can go with the small cable. I typically use like RG58, which at a certain frequency might have, 8 dB of loss per 100 feet, which is quite a bit. But what if I'm only using 10 feet of it? Well, then I have 0.8 dB. In other words, I'm fine with that. It's a short piece. So a lot of this comes down to system design and what you want to use and how you want to manage it. Because then you start wondering, okay, well, how am I going to manage this stuff? And there's also the cost. The bigger the cable is, the more expensive it is. The harder it is to run. I mean, I've dealt with a spool of 1 5/8 inch hardline that was 200 feet long, and we needed a truck to move it because it was so heavy, and so big. It was an 8-foot wide spool because you can't bend it. So there are.
So would you say
Yeah.
Would you say that you would try to get the biggest wire that you can afford and manage based on what you're trying to do with your system?
Mhm.
Or is there a
all in, all
drawback
individual.
for going too big for a small system, let's say.
No, it's all about cost, expense, and manageability, and how much power you're going to run. If I'm running teeny tiny cable and I get a kilowatt amplifier, there's a chance I'm going to fry my cable because it can't handle that much power.
Yeah.
So, it's system design. It's
Scott?
down to system design. Yeah.
I've heard it said that money is the most important engineering resource.
I agree with that. Okay, what happens as the frequency of a signal is increased? Your loss gets worse. Your loss goes up. The difference between RG58, which is really tiny cable, and 213, which is big, is that 213 has less loss, better cable. What cable has lowest loss at VHF and UHF? Air insulated hardline. Hardline is expensive. It's a pain to deal with, but it's very low loss. Source of loss in coaxial feed line, multiple connectors. The more connectors you add,
forgot the
more loss.
bowls.
High SWR, we're getting to standing wave ratio in a minute, and water intrusion into connectors. Basically, that causes corrosion. What causes failure in coaxial cables? Moisture contamination. Why should you always use ultraviolet resistant cable? Well, if something's not ultraviolet resistant, it gets cracked. If it gets cracked, you get water, you get corrosion, and your cable's bad. Air core cable. The problem with air core is that air can get wet. Solid things don't get wet so much. Air can bring moisture in, which means that if you are running an air core piece of hard line, it means you typically will pump dry nitrogen into it to keep it clean. Okay, PL259s. A PL259 is known as a UHF connector. Interestingly, UHF stands for universal high frequency, not ultra high frequency. Again, this is one of those places where things got named things because they were, and they got all screwed up as a result. UHF connectors are terrible for use at UHF. They're very, very lossy. They're not rated for those kind of frequencies. So, interesting thing to remember is a PL259 is a UHF type connector. You would only use them at HF and VHF. An RF connector that's useful above 400 megahertz, that's known as an N connector. That's a double shielded, water insulated connector. They're great for use up to about a gigahertz. Standing wave ratio. What can cause standing wave ratio issues? That would be a mismatch. You could have a broken wire. So now we're going to cover what standing wave ratio is. Standing wave ratio is a measure of how well matched one impedance is to another. So if I have a cable and I have a transmitter here and the cable goes up to an antenna like this, I have my transmission line and I have my transceiver and I have my antenna up here. Ideally, this is going to be 50 ohms. This
Hey,
is going to be 50 ohms.
Scott,
Yes.
I was just noticing that it's almost noon.
Yep. This is going to be
And-
it.
Okay, because I'm thinking SWR is important and I kind of have to leave and I didn't want to miss a whole lot of it.
Nope.
But okay,
Nope. Okay,
thanks.
so we have 50 ohms. So everything is supposed to be matched together. Now, if we have an antenna that's 50 ohms and a transmission line that's 50 ohms and a transmitter that's 50 ohms, we have a perfect match, and signals that go out get radiated and they never come back. We never see them again. But let's say that we have an antenna that has an impedance of 10 ohms. Our signal gets up here. It basically hits a discontinuity and a little bit of power goes out and some of it gets reflected back. So we actually have waves that are traveling this way and waves that are traveling this way. Using something called a directional wattmeter, which is basically a diode powered wattmeter, we can measure forward and reflected power. By knowing how much forward and reflected power we have, we can use this to calculate our standing wave ratio. The issue here is that if we have in our transistors a wave that's being generated like this, and we have another one that happens to be coming back, bouncing off of something, and it's in phase. And this is a measure of voltage, and we are operating close to our limit right here. And now all of a sudden we have another one that's being added to it right there. We can actually have so much voltage being generated in our transmitter that we take our transistors and we cause them to get fried. And this is why our transmitters typically will sense what the standing wave ratio is and intentionally protect themselves by lowering the output power, which lowers the voltage and lowers the reflected energy. Another way to fix this, make everything happy, is by adding an antenna tuner right here. An antenna tuner can sense or be tuned to see what the impedance is in the outside world and make adjustments so that the antenna, that the transmitter always sees a nice happy 50 ohms. Well, up here you have 50 ohms and 10 ohms. You have a mismatch of 5 to 1. That is very inefficient. What'll happen is that you have some energy that comes bouncing back here. When it gets back down, the antenna tuner will send it back up the line. Some of it goes out, and then some of it comes back. It gets reflected back up and back and forth and back and forth. And what will happen to most of the power that you are putting into your cable is that it just travels up and down the line, up and down the line. And because cable doesn't have zero loss, what will happen to your signal? It will just cause heating of your cable. So the worse the mismatch you have, the worse the match up here, that will exacerbate problems in your cable as far as cable loss. So lossy cable is exacerbated by high SWR. Basically, SWR is a measure of how well matched an antenna is to the transmission line.
So does that mean when you're using something like a speaker wire, that can really throw it off from your 50 ohm?
Oh yeah, very much. That's a parallel line. That's a totally different thing. Now the antenna's fine. That's still a dipole. But so now the question is, let's say I have an antenna tuner that I've put at the output of my transmitter. What is my SWR at the antenna?
Still 5 to 1.
It's still 5 to 1. That's right. The antenna tuner did not fix the problem. What did the antenna tuner do?
Protected your radio.
Protects the radio, makes the equipment happy. That's the only thing it does. It makes the equipment happy. You still have a really badly matched antenna up on the upper right. So the only way to fix that is by using less lossy cable. That can make you more tolerant to it, or by getting a better SWR. And this is going to be the last thing that we do. And I think we've pretty much covered it. An SWR is a measure of how well a load is matched to a transmission line. A 1 to 1 is a perfect SWR. 4 to 1 is an impedance mismatch. Benefit of low SWR is reduced signal loss. What happens to power loss in a feed line? We've been covering that. Turned into heat, heats up your cable. Why do most solid state transmitters reduce output power? So you don't fry your circuitry. Reduce to protect the output amplifier transistors. Which of the following should be considered when selecting a meter? So you need to know how much power it's going to be handling and the frequency at which it works, because internally it uses directional watt meters. And to determine SWR, you could also use a directional watt meter and then calculate it. If you're using an RF power meter or an SWR meter, you want to put it in the feed line. Typically, if it's a watt meter or an SWR meter, you put it close to your transmitter. Okay, now, one other thing is that something called an antenna analyzer is a non-amateur radio transmitter. It's a very low power device that puts out a signal into an antenna. The nice thing about it is that it doesn't have to be in a ham band. So it can sweep an entire range of frequencies because it's not a legal transmitter. It's outside of legality. Very, very low power, but it can sense the amount of power coming back, and it can provide you a nice graph for what the antenna looks like, even outside of the ham band. So if you have a signal, if you have a curve that looks like this, And here's the ham band that you can test for. Well, if you see that, you're not really sure where this dip is because it's outside of the ham band. By using an antenna analyzer, you can actually visualize it, which is a very helpful thing. And what is the major function of an antenna coupler? It matches the antenna system impedance to the transceiver's output impedance. The purpose of a dummy load is a 50 ohm non-inductive resistor mounted on a heatsink. It's designed to absorb transmitted energy when you're transmitting from a transmitter and turn it into heat on purpose. And why is it 50 ohms?
That's the standard.
And why is it 50 ohms non-inductive? This comes back to what we were drawing before.
So you don't transmit accidentally.
Nope. If we have our resistance over here, this is the last thing. We have our resistance axis and our impedance axis, R and X. Resistance is resistance. It'll cause a dot to be made right over here, right? That's 50 ohms. Purely resistive. What happens if we have an inductor? Inductors have a reactance that goes up this way. So if we pick a particular frequency and it causes this much inductance to occur,
You're no longer 50 ohms.
we are no longer at 50 ohms, are we? And if we change frequencies, now maybe it's up here. And now we're really not at 50 ohms anymore. And that's why we use a non-inductive resistor.
What does a non-inductive resistor look like? What's it made of? How's
Well,
it?
it can be made of carbon,
Just carbon.
know,
Yeah.
or it can be a coil of wire that never makes a full loop. It can look like this. And because it never makes a full loop, it doesn't actually have any inductance to speak of.
Hmm.
All right. Well, it's right around noon. Tomorrow's going to be a fun day. I mean that in the best way. Because
Every day's a great day.
we're now through most of the really hard math stuff.
Well, today was great because I was learning a lot about the antenna systems.
Yeah,
Learning.
antennas rock. You know why antennas rock?
Because when the wind blows, they sway back and forth.
Yeah,